Thank you. All right, welcome everyone to On the Road in the Foothills. This has been a collaborative effort of the Department of Viticulture and Enology at UC Davis and University Cooperative Extension in the Central Sierra. And thank you all for attending today's program. I want to start off by thanking, first of all, our extension partners, because without their support, we would not be able to bring you programs like this one. I'd also like to thank the people on the UCD V&E extension team, including Caroline, who you may have talked to or emailed about registration. She's also helped us out with some of the logistics of this program, and also to Anita Oberholster for her sage advice when it comes to all of these programs. I'd like to also thank Lynne Wunderlich. She's the farm advisor for the Central Sierra. That includes the foothill counties of Amador, Calaveras, El Dorado, and Tuolumne counties. And initially, this was actually a program for sort of her area. And we decided, since it was virtual, we could just open it up to everyone. I want to thank her for her generosity in opening it up for everyone to be able to participate in this program today. And I also want to thank her. We had several emails back and forth about relevant discussions that would be sort of good topics for her stakeholders to hear about. Also, I want to thank our speakers this morning for sharing their time and expertise, and all of you for attending. We have a few housekeeping items. Please stay muted during the presentations. If you'd like to ask a question, please enter it into the chat box, or you can raise your hand in Zoom to ask it live. Closed captioning is enabled. You can turn it on and off in the meeting controls down below. And then last but not least, please take a moment. So we're going to send you the recording of today's program in the next couple of days. Along with that, we're going to send you a link to complete a survey. And we'd really appreciate it if you would take the survey, because your feedback really helps us to provide relevant and informative content. All right, and the last thing I want to announce is that unfortunately, Ron Runnebaum is not able to join us today. So we have moved Anita from the last spot up to the 9:45 to 10:15 spot. So just want to let you know that. And we will take a quick break right after Anita. So the break that's actually listed here at 10:45, it'll actually be at about 10:15. So sorry for those little changes, but sometimes you just have to roll with whatever happens. So with that, I think we're going to start today's program. Thank you all very much for attending today. All right, so our first speaker today is Lynne Wunderlich, and she is the farm advisor for commercial agriculture in the Central Sierra, and she's going to be talking about local weather trends.
Excellent. Thank you, Karen, and thank you, Caroline, and all of our speakers in this collaborative effort, and for everyone who's joining us today. Trying to move to full screen, but it's not letting me. Oh, there we go. Okay. So yeah, I wanted to start out today just to give a brief update on our local weather trends. I think it's very relevant to the program that we have coming from our wonderful scientists there at UC Davis. And this first picture, this first photo is showing what we saw in some areas of the foothills and throughout the state last year as a result of some of our weather trends that we had the previous fall. So this is the delayed bud break symptom that you show here. In some cases, the primary buds were dead as a result of the previous November 2020 warm and then cold temperatures that we saw in the fall. And this was particularly severe in vines that were stressed either by drought stress or canker disease symptoms, or young vines that hadn't had a chance to harden off. So weather obviously affects not only pest management issues, but also grape quality issues. And with changing weather trends, I think we're all keenly aware of that. So it has implications both for vine growth and wine quality. Okay, so in order for us to look at weather, we obviously need to have weather data, and these come from our local weather stations. So on the left here, I'm showing you the location of the 3 CMIS stations. The CMIS stations standing for the California Irrigation Management Information System. These, here's Placerville with the star. And these are the 3 stations, CMIS stations we have in the foothills. The purpose of these stations is for evapotranspiration information for irrigation scheduling. And these are in some ways some historic stations. The Camino and the Plymouth stations have been around for a really long time. Since I arrived, one of the, what I think of as one of the achievements of my career is to help place, in the collaboration with growers, cooperating growers, and with funding from various sources, more stations throughout the foothill regions. So we now have 7 powdery mildew index stations that are hosted throughout the foothills, including these 3 in El Dorado County, Gold Hill, Lava Cap, Fairplay. And then as we move south into Amador, we have 2 in the Shenandoah Valley, the Rombauer, previously the Wrenwood Station, and Amador Eagle, and 2 also in Calaveras County, in West Point and Ironstone stations. We don't have any in Tuolumne County, unfortunately. And what you can't see here is just the variety of the topography across the foothills and the microclimates that influence the data that I'll be showing you. So here's a picture on the left of what the CMIS station looks like. It's surrounded by well-watered grass. That's the goal here, is to use the evapotranspiration from the well-watered grass to estimate baseline ET. And you can see here, this right here is the temperature sensor. It's an ambient temperature sensor, and here's the rain gauge. This is what the powdery mildew stations look like, and this is the Amador Eagle station here with the late Doug Gubler, who helped place these stations. And I wanted to just show this because the difference is that the temperature sensor for the mildew index is placed in the canopy. So the temperature is different. The sensor placement is different for the powdery mildew index stations than for the CMIS stations, but they both have rain gauges. So I'm going to be showing you some kind of maybe busy looking slides because we have so much data to show, but all of the precipitation information is presented in the same way. So this first slide shows the data from the 3 CMIS stations, the Camino and Diamond Springs and El Dorado on the top, and the Plymouth and Amador on the bottom, going back historically for, I think, 12 seasons. And that's some of the value of the CMIS stations, is that we have more data from them historically so we can compare. So this is the precipitation data for the hydro year. So the hydro year starts October 1st and goes through the fall and winter into the spring of the growing season, ending September 30th of that year. So it is meant to include the water that we would get in fall for the following growing season. So we call it the hydro year. And you can see the color of the precipitation by month here, paying attention to the green in March, where we are today. So this is where we are up to just a few days ago, including the recent rainfall that we had. And we can see here that, we're obviously in a drought, but what is the extent of the drought in the foothills? And this is what this data is showing you, as compared to perhaps the last drought that we remembered, the 13, 14, and 15 drought. And we can see here that, we're looking at a severe situation, even in comparison to the last drought that we saw, we have less water precipitation measured from all of these stations. Now, interestingly, all of these CIMA stations have measured less precip than the corresponding index PMI stations. And I'm not sure why. It could be that the CIMA stations are a little antiquated, but we are seeing a little bit more precipitation in the El Dorado, in all of the PMI rain gauges. This graph shows the El Dorado stations. So I know that for those of you out there, you're going to be focusing on your region. I'm going to show the El Dorado, the Amador, and then the Calaveras stations. The Lava Cap station, I think, is weighing in at the highest precipitation that we've seen so far, with about 27 inches. Still, less than we've seen in previous years. Gold Hill at about 24 and Fairplay at about 20. And the thing to notice here is, where historically we really did get pretty good precipitation in March, that green bar. This year, we just didn't see it. We just have not seen any good precipitation since December, which is this gray part of the graph. And thank goodness we had the December and the October rains. Okay, so that's the El Dorado station. Here are the two Amador stations. They're both fairly close together, and they're looking, as they should, pretty similar. Rombauer and Amador Eagle, both in the Shenandoah Valley, weighing in at about 20 inches this year compared to about 15 last year. And the other thing to, of course, note is, which I should have said earlier, is that, we're only here at the end of March. So we could, hopefully we will see more rain coming April and May. In the past, we have seen good precipitation in May. And that's this kind of rust-colored bar here. And then the Calaveras stations, interestingly, West Point is at a higher elevation, and it's showing about 26 inches of rain. So probably due to its location, compared to Ironstone at about 20 inches. So certainly we're in a drought, and now you knew that already, and now maybe you have a little bit more information to help guide you. I included this slide because I just wanted to remind everyone that precipitation does not equal plant available water, right? So we have to consider our local soils, that's the percent rock, the depth, and the texture are all going to affect how much water, as well as rootstock and vine age, how much water those vines can access. So I thought I'd play with, maybe dangerously here, looking at some of the temperature data. So, and I was particularly interested in any trends that I could see in fall, winter, and spring, given that we had that unusual delayed spring growth phenomena happen last season, and also the very early bud break that we're seeing this season. So this is only the Amador Eagle station data that I'm showing here, going back this year and 5 years past, looking at the monthly average air maximum temperature and the monthly average air minimum temperature for October, November, December, January, February, and March. So it's broken up by month and year. So this first would be October, November, December. We're missing some data there, so there's a gap. January, February, and March. And I guess, I'm not a meteorologist, or I don't, quite know how to interpret this data, but what I was looking for is sort of outliers. And here we certainly see the outlier, and this is, again, average temperature that we saw last, 2 Novembers ago. This average high of 86 in November of 2020. I lost my pointer. Oh, there it is. Okay. you know, followed by a low the next month. And the temperatures, the minimum temperatures were sort of even keeled pretty much throughout here. But what we're seeing here is these unusual highs responsible for, problems in growing the grapes, right? Problems in shutting down the vines for the season. The other thing that I wanted to point out here is what we're looking at this year, with average highs in February of 64. I mean, we've seen that before, but it's kind of a recent trend. And this year, an unprecedented high, average monthly high of 68 in March, accounting for this really early season bud break. All the powdery mildew index stations have already begun to accumulate the index based on the early bud break that we've seen in some varieties. Of course, it varies by your site and variety. But this is an unprecedented March 13th bud break at a vineyard in El Dorado in Chardonnay. So. And I'm having a technical, there we go. And this is my last slide. I just wanted to show the cumulative growing degree days. This is the old Winkler method of taking the average and subtracting 50 degrees from it, and just showing over time in two of the Calaveras locations, which presumably would be some of our warmest locations, how we've seen an increase in the last couple of years in the rate of growing degree days due to, of course, growing, you would assume that, growing due to the heat that we've seen. So in dark here, here's 2021, and in blue here for the West Point, 2021, 2020. 2019 was cool. So, is this a trend or not? I can't say, but certainly we've seen some things that we haven't seen before or in recent years. And this is going to, of course, affect the ripening and what you can expect for harvest dates. So with that, I'll turn it over. This last photo here is a picture of Nero de Avila, one of the heat tolerant varieties that was recommended by Vitorino when he came to visit in 2016, Vitorino Novello from Italy. We hosted him and we discussed heat tolerant varieties, and someone did plant that and it's doing quite well. So with that, I'll stop sharing.
Thank you very much, Lynn.
Thank you.
All right, next up, we have Megan Bartlett. She's an assistant professor in the Department of Viticulture and Enology at UC Davis. And today she's going to be speaking about new traits to improve rootstock drought tolerance. Take it away, Megan.
Hi, everyone. Thank you so much for having me today. Thank you all so much for coming. As Karen said, I'm going to be talking about work that my lab has been doing over the last few years to identify traits that we can use to improve drought tolerance in grape rootstocks. Rootstocks that perform well under dry conditions are a really important tool to maintain yield and quality under drought conditions or low irrigation. So here we're defining drought tolerance in a viticultural sense, where we mean rootstocks that are able to maintain adequate canopy growth and yield even under water limited conditions. You all know how much your choice of rootstock can affect the performance of your vines, where this picture is an example. On the left is the same variety grafted onto a low vigor rootstock. And the right is that same variety grafted onto a high vigor rootstock. So you can see there's a very dramatic difference in the canopy and your ability for fruit production based on your choice of rootstock. So generally the rootstocks that are high vigor are also the rootstocks that are drought tolerant. because that's an indication that that rootstock is able to reach deep water and rapidly transport it to the scion. So improving the drought tolerance of rootstocks is a really important research priority because of their importance as a tool for dealing with low irrigation conditions. And one of the things we need to do in order to improve rootstock drought tolerance is we need to be able to identify characteristics that actually confer drought tolerance. And that will enable us to facilitate breeding for more drought tolerant rootstocks. And so the goal of this study was really to zoom in on characteristics that we expected to be especially important to rootstock drought tolerance, and develop ways to assay those traits and to understand their role in drought tolerance. So we focused particularly on cellular traits that we expected to be a really critical bottleneck for drought tolerance. So the roots are a really important bottleneck for water transport, and that becomes especially true under water stress. So the roots can account for about 90% of the resistance to water movement from the soil to the canopy, even under good conditions. And that percentage can become larger as the soil becomes dry and the roots become water stressed. And so most of that resistance to water movement actually comes from the living cells inside of the root. Where if you look at a cross section of the root, this is the part of the root that's in contact with the soil. This is the water transport tissue, or the xylem, that's adapted to rapidly transport water up to the surface. Most of our work is focused on this xylem tissue, this specialized water transport tissue, but modern imaging methods and the ability to really look at how these roots are performing in a living plant kind of indicates that this band of living tissue in between the soil and the water transport tissue is actually really critical to drought responses, where these living cells are very vulnerable to drought, and kind of the failure and death in these cells as the roots dry out seems to be kind of the weakest link in rootstock drought tolerance. So the goal of our study was to understand what traits we can use to assess the drought tolerance of these living cells. And so this vulnerability to drought in these living cells comes from a couple different mechanisms. So one is that the roots actually physically shrink as they lose water. So these tissues actually physically shrink, and that process actually disconnects the roots from the soil. So this is an example here of kind of a cross section through the soil, where this is a root that was previously in well-watered conditions in contact with all of the surrounding soil. In dry conditions, it's shrunk and it's actually pulled away from the soil. And so it no longer has access to the water or nutrients in that soil. So that's one process. And the second seems to be so far specific mostly to grapevines. And that's a process where these living cells can actually undergo a cell collapse and death as the roots dry out. And that actually reduces the ability of the root to transport water from the soil to that water transport tissue. So this is an example of this kind of shrinkage over here on the right. You can see the diameter of a well-watered root versus one that's been subjected to drought stress. You can see how much it's been compressed and kind of pulled away from the sides. And this on the left is an example of this cell collapse and death, where these cells are actually kind of physically collapsing and imploding. And under well-watered conditions, all of these cells kind of provide pathways for water to move from the soil towards that water transport tissue. But as the cells collapse and die, you lose these pathways. So that means there's fewer potential pathways for water to move, and your overall ability to move water is decreased. So the goal of this study was to try to identify traits that could tell us kind of about both of these mechanisms. And so the traits I'm going to focus on today are going to be called capacitance and Turgor loss point. And so capacitance is the trait that we were using to try to assess this shrinkage. And so capacitance is the relationship between the volume of water in the root and the water potential inside the root. So as the root dries out, the water potential declines, and it also loses volume as water leaves the root. So roots that have a very large capacitance undergo a lot of shrinkage as water potential declines. And so we would expect that to be a characteristic that makes the roots drought sensitive, because they're more prone to this shrinkage and pulling away from the soil as they dehydrate. The second trait we looked at was intended to capture this cell collapse, which is called the Turgor loss point. And so the Turgor is the water pressure that holds up the inside of plant cells. You can kind of think about filling a swimming pool, where once you have a certain amount of water in the pool, you actually have enough water to hold up the sides. And that water, the force that's holding up the sides of the pool is Turgor pressure. And then in the pool, just like in the cells, as you lose water, you lose this pressure. And at some point, you no longer have enough pressure to hold up the sides, and the pool or the cell just completely collapses in on itself. And so the Turgor loss point measures the water potential of the root, at which this Turgor is equal to 0. So that's kind of measuring how water stressed the root has to be before it undergoes this cell collapse. So we would expect a more negative Turgor loss point to be a more drought tolerant root, because that would mean it maintains this Turgor under more water stressed and drier conditions. And so Turgor loss point, so Turgor is really important for root structure, because it holds up the walls, and it's also important for root growth, where this is the driving force that's kind of expanding the cells and allowing the roots to grow. So the goal of this study was to look at these traits and how they varied across commercial rootstocks. We were interested in whether there's already diversity in this trait that we can work with. And we were also interested in whether or not these traits are impacted by drought, where plants have a lot of ability to kind of manipulate their anatomy or their biochemistry in response to stress. And so we were interested in whether the rootstocks could actually improve these traits in response to a prolonged drought as a kind of acclimation mechanism. The second is we were interested in, are these traits actually related to gas exchange and biomass under water stress? Do they seem to predict the things that are important aspects of drought performance? And then I'm also going to talk about some more recent experiments. We were interested in kind of what mechanisms connect these traits to drought tolerance. Why are these traits actually conferring drought tolerance? And I'll specifically talk about capacitance a little bit more in that section. And then finally, I'm going to compare these traits between different experiments to see how consistent they are, because having these traits be consistent and predictable across rootstocks is really critical to be able to use them in breeding. You have to be able to recover kind of the same ranking in these traits in order to use them to produce new plant material. Okay, so I'm going to go over these experiments really briefly. I'm going to talk about 3 greenhouse drought experiments today, where we were using a greenhouse experiment to control the depth of the roots so that all of the rootstocks are kind of accessing the same amount of soil. And so the first experiment, we grafted 8 different commercial rootstocks onto Chardonnay. We subjected them to 2 different watering treatments, where they were watered 3 times a week. They were either kind of rewatered up to a almost saturated point, or they were kind of consistently rewatered to a water deficit state for several months. We destructively sampled the plants to measure these traits, and then we also monitored gas exchange and water potential over the experiment, and then measured growth and biomass at the end. The second experiment, we zoomed in on 2 rootstocks that had very different traits in the first experiment. So that's going to be 420A and 140RU. I'll talk more about that in a bit, where we subjected both of these treatments to a really rapid drought, and we measured kind of what the impacts were on the performance in a more detailed way. How did it affect the ability of the plant to transport water? And then finally, I'm going to talk about a third experiment where we grafted 4 of the same rootstocks onto a different scion. We subjected them to watering treatments again, and we wanted to see, do we get repeatable trait measurements? Are these reliable and consistent traits that we can screen for in breeding? And the first thing we found is that there was a significant amount of diversity in these traits among rootstocks. And we also found that the rootstocks were able to adjust these traits to improve their drought tolerance and acclimate to water stress. So these are the 8 different rootstocks we were using in this experiment, where 4 of them are considered to be drought sensitive in field conditions. So that's things like 420A, 5C, Riparia, 10114, and then 4 are considered to be drought tolerant. So that's things like Ramsey, 140 rupestris, 1103P, and 110R. And so you can, the blue bars here are showing the results from the well-watered treatment, and the gray bars are showing the results from the water stress treatment. And so you can see there's a significant amount of diversity in these traits across the rootstocks, where the Turgor loss point varies about threefold, where these are the rootstocks that are most sensitive to losing Turgor. You would expect them to undergo cell collapse under less dry conditions. And the same is also true of capacitance, where there's also a significant amount of diversity in that trait, where these rootstocks that have very high capacitance, you would expect to also be very sensitive to drought because they are undergoing this shrinkage and collapse earlier under drought. And then comparing the blue bars to the gray bars, you see that the plants were able to really adjust these traits when they were given several months to acclimate to drought. So they made their Turgor loss points more negative, which indicates they're less vulnerable to the cell collapse. And they also made this capacitance smaller, which indicates that they are less prone to this root shrinkage. And so another promising finding from this was that the trait capacitance was correlated with your gas exchange during drought. So this is showing the stomatal conductance of the scion versus the average Turgor loss point or capacitance of the rootstock. So each point is the average for a different rootstock over the whole period. The blue is well watered and the black is drought. And so you can see that the capacitance in the droughted plants was significantly correlated with the stomatal conductance of the scion, where the rootstocks that had a very high capacitance were very prone to this root shrinkage, were also forced to close their stomata under the drought conditions. So that suggests they're not able to keep taking up water from the soil and replacing the water that they lose to transpiration. We did not find a relationship between the stomatal conductance and the Turgor loss point. And we did find a very weak relationship between the Turgor loss point and the transpiration of the entire plant. But mostly we found a relationship between the Turgor loss point and the size of the root system under drought. Where on the right, this is showing the relationship between the whole plant evapotranspiration and Turgor loss point. There's a very weak but significant relationship between having a more negative Turgor loss point and maintaining slightly more evapotranspiration. But really this relationship is better for between Turgor loss point and the size of the root system, where the rootstocks that had a more negative Turgor loss point also had larger root systems under water stress. And so that goes along with what we would expect, where these rootstocks are able to kind of maintain this Turgor pressure and keep up powering cell expansion for growth under stress. And then we wanted to zoom in on two of the rootstocks with very different capacitance values to see if we actually see improved water transport in the rootstock with a low capacitance, which is what we would expect. So we compared 420A and 140 rupestris, where 140A generally has a higher capacitance and a less negative Turgor loss point than 140 RU. And so what we did is we subjected them to a really rapid drought, so they didn't have time to acclimate. So we had, for one treatment, we had plants that we didn't allow to acclimate. And for the second treatment, we had plants that we did allow to acclimate, sorry. So the blue points are showing plants that were hit with an immediate drought. The black points are showing plants that were allowed to acclimate for a few weeks, then hit with a drought. And so this is showing the relationship between the hydraulic conductance of the plant and the water content of the pot. So these are logged, so the values are a little bit odd. But essentially what it's showing is that the ability of the plant to transport water declined more quickly as the pots dried out in the rootstock that had a higher capacitance, that 420A. So that suggests that that having that really high shrinkage under water stress also limits the ability of that rootstock to keep up water transport from the soil to the canopy. So that suggests that we have hit on a trait that's related to your water transport ability. And then We also found that the Turgor loss point was really strongly correlated between experiments, but unfortunately for capacitance, it seems like this is potentially much more sensitive to your growing conditions. So this is the relationship between the Turgor loss point in our first experiment and our third experiment. So you can see there, and each point is a different rootstock. You can see they're very well correlated for Turgor loss point, which is great because it means if you repeat the screening over and over again, you'll get consistency in your differences between your genotypes or your varieties. But capacitance was kind of much more scattered. And I'll talk a little bit about why I think this is in a couple minutes. But it's kind of a knock against breeding for capacitance. It suggests we're likely to have some difficulties unless we really figure out how to standardize our growing conditions. Okay, so overall, what we found from this work is that root cellular traits are important for understanding rootstock drought tolerance, where we found relationships between the capacitance and the Turgor loss point of these living cells in the root to be well correlated with the gas exchange and the biomass of the root system under water stress. So we found that the roots with a lower capacitance seem to be able to maintain a hydraulic connection to the soil. They're able to keep up their water transport under drier conditions. So that suggests that that those rootstocks have a greater capacity to extract water from drying soil. So you can think about extraction as the roots have already kind of moved into a zone of soil, and how much water can they actually kind of drag out of that zone of soil. And Turgor loss point seems to be related to kind of another characteristic of rootstocks, which is soil exploration, where the rootstocks with a lower Turgor loss point produced larger root systems. So that suggests they're able to kind of keep moving into new zones of the soil and taking up water from those zones under dry conditions. And we also found that Turgor loss point was very highly predictable, but capacitance could potentially be too sensitive to growing conditions to be a good target for breeding. But there's kind of evidence that being able to increase your extraction capacity by targeting capacitance could potentially be really important for drought tolerance for thinking about the life cycle of a grapevine, where very little root growth actually takes place after veraison, specifically to avoid resource competition with the fruit. And so this is showing kind of the results for the amount of root growth over the course of the year for from two different experiments for two different rootstocks. And so you can see relatively little of the root growth actually takes place in that period of veraison to harvest, which is often the driest part of the growing season for grapevines. So that suggests that exactly at the time when you're most water stressed is at the time when you have kind of the least ability to grow new roots and explore new areas of the soil. So that suggests that being better at taking up water from the soil you're already in is potentially a really important characteristic for drought tolerant rootstocks. There's also a potential for capacitance to kind of have other upstream effects on the scion, where your root shrinkage under drought has actually been kind of connected to different kinds of hormonal signaling, which are hypothesized to be important for stomatal closure and ripening. So this is kind of something that's under debate, how much of this hormonal signaling is actually moving from roots up to the scion. That's kind of an open area of research in grapevines. But it suggests a potential mechanism for selecting for kind of different vulnerability to shrinkage to kind of have these upstream effects on the time of your ripening and the regulation of your water use in the scion. So that's kind of an interesting area of future work. So Turgor loss point is also known to be important to the lifespan of the roots, which could be another important consideration for thinking about selection for these traits. So we know from other species that this is kind of a general pattern where a lower Turgor loss point facilitates root growth under water stress. And there's also results from grapevines suggesting that it keeps the roots alive in drier soil for longer, where having a more negative Turgor loss point and the roots up at the surface kind of helps those roots pull water away from the roots that are in wetter soil. And that kind of helps keep those roots alive under dry conditions up at the surface. And so we've always assumed that this is a really beneficial adaptation because more of your root system is alive. But I think that we have to kind of think about what that means in the context of the whole plant, where the metabolism of these roots is very expensive. Under a drought, it can use up to about 3/4 of your photosynthesis, just keeping roots alive. So I think we need to think about, is it always that a more negative turgor loss point is always better? Or should we start to think about, can we produce rootstocks that maybe kind of preferentially dump roots up at the surface in order to send more resources down to root growth at depth where the soil is wetter? So I think that's an important consideration for these traits. Kind of, is more always more for these traits, or is there kind of an intermediate that's optimum for these traits? And then finally, is turgor loss point necessarily a better candidate for breeding than capacitance? So capacitance appears to be very sensitive to the dryness of the soil in which the plants were grown. So this is showing the relationship between the capacitance and the pre-dawn water potential in the two different experiments. And basically the takeaway here is that our first experiment, we were much better at kind of controlling the dryness of the soil, where it was very similar among all of the rootstocks in the wet treatment, and then very similar among all the rootstocks in the dry treatment. That's these kind of green points here, because we had much bigger plants in smaller pots. In the most recent experiment, we were kind of doing the opposite. I think we ended up with more differences in rooting depth. So some of the rootstocks, even though they were receiving the same amount of water, they ended up a little bit less water stressed or more water stressed than others. So that suggests that we need to think carefully about the environment when we're doing greenhouse assays for this trait, if we're going to actually use this trait in breeding. So we need kind of more information on whether capacitance is consistent under different growing conditions, including things like soil type and scion, because we also used a different scion in these two experiments. And then finally, some of the future directions we're going in this work, I talked about this a little bit, is kind of what values are actually optimal for drought performance. Do we always want the lowest values? Is there an intermediate that's kind of maximally effective? And how do the most effective values depend on the soil type or the scion cultivar? We're also interested in understanding what actually makes a rootstock have a lower capacitance or a lower turgor loss point. What kind of anatomy or biochemistry are we looking for to kind of create rootstocks with lower trait values? And then finally, all these experiments took place in pots. And we're interested in how these traits are kind of different within a very heterogeneous rootstock that you have in a very deeply rooted root zone like you get in the field. So for example, can we think about the roots at the surface are more like the ones we measured in the water stress treatment, while the roots at depth are more like the ones in the well-watered treatment? And does that variation within the root system matter? Is there a particular amount of variation or kind of variation that we should be selecting for in our rootstocks? And how does this kind of affect the ability of the vine to access this water at depth? Okay, so with that, I want to thank the people who have funded this work, especially the American Vineyard Foundation, Novavine for donating some of the vines in these experiments. I want to thank the people in my lab who have conducted this work, and the department for their support. And I guess we have a couple minutes for questions, or I'll be back for the kind of question wrap up at the end. So thank you all so much for coming.
So does anyone have any questions for Megan? You explained it all so well.
Or it's just early.
I'm not seeing anything in the chat. I don't see any. Oh, Lynne has a question.
Yeah. Great.
Go ahead.
Maybe I'll just talk instead of, so Megan, thank you for that presentation. Wow, so much information. I was trying to take it all in. My question has to do with how we can maybe better transfer this type of information on rootstock traits that are important to growers in their selection of rootstocks. Because I'm thinking about how, and maybe you're not there yet, because this is you're early in your career and in your research, but I'm thinking about how simplified our charts are for rootstock selection. I think there's just a column that says drought tolerance, you know, and so, you know, we have, there's so much more to rootstock selection. I mean, there's phylloxera resistance, you know, there's sort of all the basics, but now we're getting into some very specific traits that would depend on maybe your soil depth and other aspects. Do you have any thoughts about?
Yeah, I think that's a great question. And you're right, we are a little bit early here. Like my thought is kind of, this could be work that informs breeding for more drought tolerant rootstocks, because then we have a better idea of how to screen through all of the material that we produce in breeding. We can actually kind of narrow down potentially genes that are related to rootstock drought tolerance, and that would really accelerate our ability to breed for improved rootstocks. But I also think that having a better idea of what characteristics of the rootstock, like kind of how they vary and how that plays out in different soil types or for different scion cultivars, could potentially be really informative. Or we could think about, oh, this is maybe this is a particular range of rootstocks that's targeted more towards dry farming versus irrigation, because that kind of affects, like, you know, your relationship between water in the surface and water at depth. You might want to keep these roots at the surface alive if you're going to be regularly irrigating, but you may not. You may want to completely dump them if you're in a dry farming system. So that's an example of something we could think about. Or like if there are relationships between this root shrinkage and the structure and properties of your soil, perhaps, you know, we even create rootstocks that are targeted to different soil types, you know, something like that. So yeah, I think this does kind of open up the ability to be more specific and more targeted with our rootstock selection down the road.
Right. Great. Thank you.
Sure.
All right, thank you very much, Megan. All right, so this is where we're varying the program a little bit from the original schedule that was sent out. Anita Oberholster is going to be our next speaker, and she is the Vice Chair and Associate Professor of Cooperative Extension in Enology in the Department of Viticulture and Enology at UC Davis. And today she's going to be speaking about grape smoke exposure mitigation from vineyard to winery.
Thank you, Karen. Okay, I think that should work. I just shared my screen. So yeah, Lynn asked me to talk about smoke exposure. As unfortunately, a lot of people in the foothills obviously were impacted by grape smoke exposure in 2021. And then 2020, it felt like it was almost everybody else. This is a very, very important issue. She asked me to focus more on mitigation, and both in the vineyard and the winery. But I will start off with the basic science like I always do, because I don't want anyone to misunderstand or take out of context what I'm saying. It's definitely a work in progress. So a lot of what I'm going to tell you is what we do and do not know. But, you know, information is key so that you can at least make informed decisions. So
rescheduling your appointment.
There we go. So what is smoke taint? So smoke taint, you know, a taint is seen as something that comes from outside and overpowers a wine and decreases the quality and many times make it one-dimensional. So in the case of grape smoke exposure, this could be that you have an overpowering, smoky, burnt, campfire, medicinal, earthy character. And it could be bacon, sweet barbecue. There's an exhaustive, there's a long list. However, for me, that's distinctive to smoke taint because there's other things that can also cause some of these aromas. Key for me to grape smoke exposure that you will get from nowhere else is a lingering retronasal ashtray character. So it's something that you perceive in your mouth. It's at the back of your throat. And that is really important because, and it's like an ashy campfire, old cigarette smoke perception. And obviously, if you listen to those descriptors, you can understand why that is not a quality or an attribute that anybody's looking for in a wine. But that's what I see as distinctive to what I would call smoke taint. So what happens during a wildfire? During a wildfire, you have a lot of vegetation burning. And if you think of wood, 15 to 25% of wood is lignin. Now, if you look there on the screen, this is the structure of lignin. When you have a fire and it burns, you get thermal degradation. So it basically breaks up into a lot of these aromatic compounds with OH groups on top of them, and that is a phenol. So the one I'm showing you here is something we all have heard about by now, guaiacol. So that's an example of guaiacol. But you can see there's many other volatile phenols that can be released because they're volatile during a wildfire. And depending on the fuel source, yes, the composition of the volatile phenols that's being released can change. Now, when they're released into the air, they can travel on air currents, temperature difference, air movement, a lot of things predict in what direction it goes and how far it can go. However, it actually breaks down pretty quickly. It can absorb onto debris in the air, like ash, and then disperse with the particulate matter, with air movement, etc. So what happens when you have a vineyard and you have grape berries on the vine? If you have an excessive amount of volatile phenols, or we do not know exactly how much volatile phenols you need in the atmosphere around the berry to cause significant absorption, this happens through the berry skin. It's not on the inside, it goes into the skin itself. And then inside the skin, there are enzymes that actually would glycosylate. Glycosylate means that you add sugar to a compound. And we think this happens due to a defense mechanism of the plant. Now, what can happen is you can have enzymes, glycosylates, that will basically, or glycosyl transferase, I should say, that can add 1, 2, or 3 sugars to these volatile phenols. Now, think about it. You have a range of different volatile phenols. They can have a range of either 1, 2, or 3 of various sugars attached to it. You can see there's a lot of potential compounds out there. To complicate the story even more, all these compounds are naturally present in grapes. So you can get both the free volatile phenols and the bound volatile phenols in the grapes, okay? So, and the natural amount present, we know depends on variety. We know it depends on season because we know climate impacts synthesis of most compounds in the grapes because enzymes get up and down regulated through light, through temperature, etc. So this is very important to remember. And we do not yet know the impact of site. So basically of terroir in general. Also, these compounds can absorb onto the leaves. So they can absorb onto the leaves, onto the grapes, and that's it. They don't seem to absorb onto the hard, woody parts. Now, currently, most labs will look at these 7 main volatile phenols. Now, this is based on work that was done at the Australian Wine Research Institute. They've been doing work in this since the early 2000s. And they look at these 7 compounds, and there's 6 individual bound to glycosides that there are actually reference standards for that you can buy so that you can quantify them accurately. So when you do extended panel of free, you'll at least get the 7. And if you do an individual bound, you should get at least 6 individual compounds. But if you think about this is 13 compounds of potential of hundreds of compounds. Now, the Australian Research Institute has looked at this, and they said the predictive power using these 2 is about 70%. So just understand that there is a gray area, even if you analyze your grapes by the most extensive methods that's available commercially. So I do want to talk a little bit about the different testing methods because I get a lot of questions about this. So for free volatile phenols, you need a gas chromatographer and mass spectrometer. Okay. Now, a lot of the commercial labs out there will do free and total because it uses the same piece of equipment and you can use the same technician can run it, obviously both methods. So what it means is they do analysis of the free volatiles, then they do a hydrolysis process where they try and hydrolyze all the bound to the free. Now you can do this by enzymes, but the enzymatic methods, they're varied and they don't work all that well. Most labs would do like 100 degrees after they acidified the grape matrix or the wine matrix to a pH of 1. Now I can tell you, we've looked at this. It doesn't hydrolyze everything, okay? The hydrolysis efficiency, depending on the bound compound, is variable. It depends on the amount of sugars, and it also depends on what volatile phenol that sugar is attached to. We also don't know if it doesn't hydrolyze more than what actually contribute to smoke day. The value of free in total is, there's more labs that do this, it's slightly cheaper, and that if you have built up your own database of what that total number means. So in a baseline year, this is the total number that you have for this variety. Then in a year that you made wines or somebody else made wines, you got the feedback that it was smoke impacted, you go, okay, my total number was this, it's too much. That still has value. If you do individual bound, you get more accurate data because it's quantitative for specific bound compounds, but it's only of 6 compounds. And that prediction is pretty good, but it's not 100%. So that's something to consider. There's the same thing. Over years, you can build a database of this is what's normal for your different grape varieties, and this is what was high enough so that it actually resulted in a wine that was impacted. Now, you definitely need to do bound. We have learned that sometimes grapes have almost nothing in the free form and everything is in the bound form. Why we still do free is because it does give you a slightly better picture. There are years that there's a little bit more in the free than usual. And for crop insurance currently, they still look at the free number, and there's many contracts that still look at the free number. So you sort of need both. But definitely do the bound. The bound is very, very important. It's more predictive of the potential amount of smoke compounds that's in your grapes that can be released during the lifetime of the wine. I would say whatever methodology you use, stick to it. I would even suggest stick to the same lab, because the lab methods are all good, but sample prep can have a huge impact on the results. You know, how much do they homogenize those grapes? How long do they allow those grapes to extract before they analyze the juice or the homogenate for these compounds? Those variables can have a huge impact in your final results. So this is something also to think. When you deliver samples to a lab, always do it in the same way if you can. The best way really is to take a sample, put it in your freezer, and when you send it to the lab or take it to the lab, make sure that it arrives there still frozen, so that you know that it was intact and that you didn't impact the maceration time of the skins and the juice before it even arrived at the lab. Something else I want to say, for ISO accredited labs, most of the time they need to show that they can reproducibly have the same number with like a 5% variability. Okay, nothing is exact. There are acceptable variability even for analytical equipment. Now, what that 5% mean, for instance, is if you have a contract that says that you need a alcohol number of below 2 or 2 and below to say that your grapes were not impacted. If you get a number of 2, 2.1 and 1.9 are both in that 5% margin, meaning in reality, the 1.9, 2, and 2.1 is the same number. So when you get your results back from the lab, at the bottom somewhere, they will say what was their acceptable standard deviation for each compound. And if it isn't on your results sheet, ask the lab. They need to be able to provide you with that. That gives you an idea of how to interpret the results. So I also get a lot of questions about grape smoke exposure risk. Now, we are trying to answer this question. It's really, really complex. Currently, all we can tell you, the fresher the smoke, the greater the risk. There is not a good correlation between AQI measurements and smoke taint risk. AQI is heavily impacted by particulate matter. How much particulate matter is there? Now, the particulate matter is ash and other things. That is not volatile phenols. We know volatile phenols break down within hours in the gas phase, okay? So this is why we say fresh smoke. However, when they do absorb onto droplets, onto particulate matter, it does change that breakdown. So that is what we know. So the 24 hours is based more on anecdotal data. from other fires and talking to people, we found out that if it's less than 24 hours, you still have a risk. There's people that have been exposed to heavy smoke, but the smoke was over 24 hours old and they had no impact, even though everybody expected it. So this is where that 24 hours come from. At this point in time, because we do not have more accurate ways to determine risk, we basically say, if you had smoke exposure, you need to test. However, if you were in Paso Robles and the fire was in the Foothills and the smoke got to you 3 days later, I'm really not concerned. The same for Napa due to the Foothills fires. However, I understand, like in 2020, there were so many fires going on, you had no idea what was fresh and what was old smoke. And then obviously, this is why we still say, just measure if you can, or just throw a sample into your freezer. And if you need to, you can go back to that sample and analyze it. Also, there was a study in Australia where they, for 3 years, looked at Merlot vines, and they intentionally smoked them at different growth phases. And the study said, oh, they were susceptible to smoke at any point in time, but farm variation to harvest, it was more susceptible. And then people seem to have gotten from that, oh, you're only sensitive from variation onwards. And that's not what it means at all. Or that if you're overripe, then you're not sensitive either. That's not what it means either. It just means between variation and harvest, it's a little bit more sensitive. There's plenty of vineyards and examples in Australia of vineyards that were only exposed at rock hard pea size to fresh smoke and had made wines that were heavily impacted. So just assume if you have a berry on the vine that you have a risk. The good news here is, as I mentioned, it absorbs onto the berries and onto the leaves, meaning it doesn't overwinter. The next year you start afresh. The only impact on the vine is potentially yield and other things. If the fire came very close and there was a heat impact, we still don't really understand the impact of long periods of smoke exposure or sequential exposures to smoke. We know most of the time, if it's exposed to smoke, most studies looked at this, then if the smoke clears, the vine actually recovers very quickly. But most of these studies didn't look at extensive periods of smoke, and it didn't really look at repeated exposures to smoke. So that's something we still need to address as well. So I don't know, some of you might have heard of the SCRI grant, CAP grant that we got. Oregon State University is the main institution with UCD and Washington State University collaborating. So it seems like a lot of money, but it's a long list of PIs over 4 years. And the main focus here is this: develop sensors, low-cost sensors, and a sensor network for real-time risk assessment. So the idea here is, can we put a sensor in a vineyard? And it will be able to give you through an app indicator of yes to no of risk. Meaning, where I say now everybody has to test if you had some smoke, can a sensor tell you yes, no for risk? So we cut down the amount of testing that need to be done. I mean, that would be really important, so our labs do not get inundated again, and it will save you a lot of money. The other thing we're trying to do is link environmental, chemical, and sensory data for predictive modeling of risk. So we're working with atmospheric guys. They're looking at volatile phenol breakdown in the air, how atmospheric conditions will influence this. We're trying to link atmospheric data to these sensors to improve the readings from these sensors so that they can predict risk as well. And we're really doing almost what I would call the life cycle, but basically looking at how can we correlate berry composition and wine sensory threshold data to the measurements we got from the air and in the sensors. So mitigation in the vineyard, what can and cannot we can't do. So we know washing grapes to remove volatile phenols on the outside doesn't do anything, right? It's not on the outside, it's inside. People have even washed it with organic solvents in a lab, and I can tell you, researchers, and it doesn't do anything. The only thing we are concerned about is ash. We're still trying to investigate what is the importance of ash in the vineyard. Now, in 2020, we actually had a lot of ash in our vineyards here at the Robin Mondavi Institute. And we collected that ash and analyzed it over a week. Now, this is in laboratory conditions. It's sealed, and you put it on a GCMS at 50 degrees to exposure of a fiber. And we saw that it released some volatile phenols up to a week. Okay, but is that enough? Will that ash release enough volatile phenols to change the atmosphere around the berry to really force more volatile phenol absorption? Should you be washing that off, rinsing that off? Now, here's the thing. Wet ash actually releases more volatile phenols than dry ash. So, and it's very difficult to remove. And sometimes you're just washing it into the grape cluster. Or if you're successful, say, to wash it off. Now it's lying on the canopy floor, releasing volatile phenols. Did you improve anything? So at this point in time, we're not making any recommendation regarding washing off ash. So what we did in 2021, and you know, unfortunately, we're still trying to analyze all these grapes, is we made ash and we put it around the bunches and we folded it in a nut milk bag. And we exposed these grapes to ash that was 0, 4 hours, 1, 3, and 7 days old. And we're going to see, and this was an excessive amount, seriously. So it's basically a worst case scenario thing. If we see anything here, then we will go to more realistic. But if we see nothing here, I'm going to go, nah, perhaps I'm not really all that concerned about ash and releasing volatile phenols in the vineyard. Then we also did small scale fermentations with ash at different ages. So we did 4 hours, 1, 3, and 7 days old ash, and added it to some micro fermentations and did that. So I still need to analyze those grapes or those wines, but I can tell you this. Tom Collins did a similar thing in a different way, which is great. So I'm going to see if our data actually support each other. He added about 0.25 grams per liter of ash to a TJ fermenter, so larger, about 30-gallon size. And what he saw is he did see an increase in guaiaco and full-methyl guaiaco levels. He hasn't done sensory that I know of, but he did see some increase. He only used ash of 1 day and 7 days old. So 1 day, he did see an increase in numbers. That doesn't mean it relates to sensory increase, but he did see an increase. And the amount of ash he added was quite significant. At 7 days, he didn't see any increase. So yes, so there's perhaps a concern for fresh ash. So currently, this is what we don't know. I say, if you have fresh ash on your grapes, that's visually there. So there's enough there that you can see it. And you're harvesting and processing in the vineyard, and you have the capability to try and rinse this ash off at the winery, you want to do it. Perhaps want to try and do it. Who knows? Can also tell you want to remove mold, you want to remove leaves. Tom Collins also did fermentations where he actually added smoke exposed leaves to the fermentation. And yes, that did result in an increase in volatile phenols as well. So the other thing of looking at mitigation in the vineyard at this stage is really looking at barrier sprays. Now, kaolin was investigated by the Australians a few years back on 3 varieties, Merlot, Sauvignon Blanc, and Chardonnay. And they only saw some decrease in volatile phenols for Merlot. Now, that's always strange when you only see some in some variety and not another. When I talked to them, they said they think it is because they had better coverage of the kaolin on the Merlot grapes, not on the Sauvignon Blanc and Chardonnay, because generally in the vineyard, you get about 30 to 40% coverage. They didn't specifically note that or investigate that as a variable. So this is after the fact that what they're trying to interpret their data. Now, biofilms, we know in British Columbia, Matt Nutheden and Wes Zandberg did a study where they sprayed Pinot Noir with Parka. That's a phospholipid cuticle that gets sprayed on to prevent cracking in cranberries. And as controls, they also applied 2 fungicides. Basically, it was one was essential oil. And the fungicides made it worse, actually absorbed more volatile phenols, but the Parka showed like a 300% reduction in volatile phenols, and everybody said, oh, this is wonderful. Now, in these studies with the kaolin and the biofilm, they sprayed the barrier spray on 7 days before intentional smoke exposure. When Wesley did the study again, he applied Parka 1, 7, and 14 days prior to smoke exposure, and it made it worse. So what's going on? And when he did the fungicides, it also made it worse. And we're getting this idea that If there's something wet that didn't dry, it increases the surface area potentially of the berry, allowing more absorption to take place. So in the first place, we don't want anybody to spray anything while there's smoke in the air. These things would be preventative. You need to apply them long in advance, and they need to be bone dry before any smoke exposure. And so they didn't get good results. Something else is they say they had wet, cold conditions. So I'm not sure that the parka dried properly or that it stayed on. And the other thing is, it's not clear whether they rinsed the samples. Now, this is something that Tom Collins found out. And here in our labs, we always, when we apply something, we rinse it off before we do analytics. He actually had also been studying kaolin and been getting very variable results until he, I think it was last year, that he actually took the grapes and he did small scale fermentations. And in some, he didn't remove the kaolin, and in others, he did remove the kaolin. And those that didn't remove the kaolin, the volatile phenol absorption with intentional smoking was lower. So the kaolin did something, but those that he didn't remove it was still high like the controls. So it's not that it prevents the volatile phenols from absorbing. The barrier itself seems to be absorbing the volatile phenols. So if it's present in your winemaking, you're not actually improving anything. And so this is the problem. How do you get good coverage in a vineyard? How long before smoke exposure do you apply it? And then how often do you need to apply it so that it is a good barrier in case you get smoke exposure? And how do you properly remove it? Because I know that it's pretty difficult to remove it in the vineyard. I mean, I saw photos of Tom trying to do this, and it is really, really, you can still see the streaks of white when he sprayed it with water in the vineyard. So all these things are very, very important. So what I did in the 2021 harvest, I get a lot of requests of people that have potential barrier sprays and think it may be a solution for smoke exposure. So I evaluated quite a few of these and some of my own ideas. We looked at 12 different barrier sprays in total with a control. And we're still looking at the data, but I can tell you now at this point, kaolin is the only one that sort of showed good promise. And this is by dipping the bunches in the barrier spray. So there is not a question of not having full coverage. And obviously in a lab, rinsing everything off before we do an analysis. And the only one that we so far, we think show promise is kaolin, but we're still busy looking at all the data. If anything else show promise, we will do some randomized field trials in 2022. So what happens during fermentation? These compounds, like I say, they are glycosylated. Think of anthocyanins and red grapes. You know, if you crush the fruit, immediately you see the color coming out. And anthocyanins extract very quickly within the first 5 days. So studies that actually looked at the extraction of volatile phenols saw the same thing. They extract very quickly within the first 80% in the first 5 days of skin contact. The other thing to remember is in the beginning, there is glycosidase, enzymes in your berry that will cleave some of the bound to free naturally. So we see this increase of bound to free during winemaking, and also at the sitting medium of wine, there can be slow hydrolysis with aging, but it's very, very small. Okay, it's pretty stable during aging, but it can still change, and we don't really know how much that small change can impact sensory because it's a synergistic impact. It's not just one compound. All these compounds have an impact on each other. So I did a study, and Australians looked at this, about 25 to 30% release of your bound glycosides during winemaking to post-malolactic fermentation. Now, something to remember, you need to worry about both the free and the bound, okay? Because what happens is, it seems we have enzymes in our saliva, and they can hydrolyze the bound. And that plays a critical role, we think, in observing that retronasal ashtray character. Is that free volatile phenols that you're perceiving and the bound being released, giving you that ashy character? Because if we try to mimic that by just adding free volatile phenols in different combinations to wines, we can never do it. Something else to remember, matrix effects. This is the other reason why smoke perception can change with aging of wine. We know that a lot of phenolics can help hide the smoke. A lot of fruity aromas can hide the smoke. Green aromas uplifts the smoke. We know higher alcohol and at least 3 grams per liter of sugar or higher will actually inhibit the enzymes in your saliva and could reduce the perception of smoke taint. So mitigation in the winery, when I started my smoke taint research, that was in 2017 because one of my Red Blotch vineyard trials were impacted by the fires in Napa in 2017. So that's changed the Australians. They've done a study looking at different yeasts, and they've seen a couple of the yeast, the sensory panels showed a decrease in smoke expression. They said you need to use oak additions like lightly toasted that have no smoky or any kind of nutty kind of aromas that can make the smoke impression worse, but something that can complement and hide it. And they recommended allergic tannins to add. And they also recommended lower fermentation temperatures. And so basically I did a study, but this is over different years, different varieties. And a lot of their conditions weren't really very similar to commercial conditions here, commercial winemaking conditions. So I tried to use very similar grapes. These were all Cabernet Sauvignon. And I did, this is using our TJ's triplicate fermentations. I looked at different yeast. And I looked at 2 oak chips types and a allergic tannin. I looked at different fermentation temperatures, but they all had exactly the same skin contact, and that was 7 days. The cold soak, I did a 7-day cold soak, press, and then fermented it. And then this is something Lafort wanted me to try, is using an enzyme to get all the color out 3 days, add a tannin to stabilize the color, press the must, and then just finish fermentation with the fermenting must without the pomace. Now I can tell you this didn't work because anything that gets the color out also get all the volatile phenols out. I also found that with a skin contact time of 7 days, this didn't matter. There really wasn't significant difference by sensory in smoke impression. This didn't have an impact. This did, the oak chips did camouflage it on the nose for a while, but as the wine evolved, it came back. And it's really difficult to hide that retronasal ashtray character. Different yeast didn't have a huge impact. I did have one that looked a little bit better. I don't even want to say which one because the Australians found different yeast to be better. That was my worst yeast because, you know, yeast have some glycosidase activity and they can cleave some of the bound compounds and other not. It's small differences that I don't think really during the whole lifetime of the wine makes a huge difference. Perhaps these things can have an impact when you have a grapes that have low smoke exposure and it's in that maybe not impacted. You can adapt your winemaking style to, yes, add some oak that has neutral, low toasting, can add some complexity to the nose. You know, experiment with different yeast, right? And you may do all these kind of things and it may help. Each thing will help a little bit, but none of this is like an overall solution for smoke impact, if I can put it that way. And this is why, you know, because they're in the skin, for white wines, we say handpick, limit skin contact. Now, obviously, this is not always possible, but that is recommended, and having no mog in your fermentations when you ferment. In red wines, I said from the start, just make the best wine you can. I mean, machine harvesting doesn't matter for reds because you can anyway ferment them in contact with the skins. I'd rather you have as much phenolics and as much aroma compounds in there as possible, because if you have to treat, treatments lack specificity and they're going to take color out. They're going to take some of the body out. So you rather want more there. Now, if rosé is an option for you, an economic viable option, you could try making a rosé, really limiting skin contact. You will get less of the volatile phenols in your fermenting must. But here's the thing to remember, matrix impact. The amount of volatile phenols that can be in a full-bodied red wine without showing any smoke impact is much higher than the amount of volatile phenols that can be in a rosé that has a much simpler matrix before it can show smoke impact. So that, just remember that. it won't be the same number because matrix have a huge impact. Something else that I see a lot in white wines is this. Because you can make white wines without skin contact, you can make a wine that is not smoke impacted, and you even can make a good wine. But sometimes you get that sub-threshold smoke taint. So it's not smoke taint because you can't identify it as smoke taint. It doesn't have smoky aromas. It doesn't have the ashtray. But I call it sub-threshold because it's just muted fruit. You get this hole in the mid palate. There's this weird, unstructured bitterness at the back of your throat, and like a tip of the tongue astringency. And that's something I see sometimes with grapes that have a very slow smoke impact. Also, when we do dilution studies where we have the same wine, smoke impacted and not impacted, you dilute it in just 1% of a heavily smoke impacted wine, you start seeing, even if you can't see the smoke itself, you start seeing that muted fruit. You start seeing that body impact. It's very, very interesting. And we don't know why. Scientifically, we can't really explain it at this point in time. So then I did look at what was available in 2018, 2019 was amelioration options, right? So you did your best you can. You still ended up with a smoke impacted wine. What do you do now? Australians screened a lot of enzymes. I screened some enzymes. I only did 4 and only applied it within the low and high range of what the companies, the enzyme companies recommend. And I didn't see any impact. I did it on wine. So the alcohol could have definitely impacted the activity of the enzymes. Those that have used it in juice, it seems to be more effective on monoglycosides. And unfortunately, most of the bound is not monoglycosides. They're mostly di and tri, it seems. So it can have a small impact, but once again, it's not going to be your miracle cure. Then if you look at fining, Australia did a big screening of 12 different, I think, activated charcoals showing which ones work the best for juice fining, which ones work the best for wine fining. And then molecular imprinted polymers. So this is something that was actually developed to remove breath from wine. And it's very interesting. They use the molecular imprinting technique to make a polymer with a cavity that has an affinity for your template molecule. So basically, your template molecule, if you're trying to take volatile phenols out, would be something, one of the volatile phenols, right? And hopefully it will catch most of the volatile phenols that looks very similar. The reverse osmosis, we did the standard process, and they also developed a standard differential filtration method where they basically use the membranes of different molecular weight cutoffs to get like a more higher molecular weight fraction that they would separately treat through a proprietary resin and then add back together, basically trying not to over-treat the whole wine, but only the fraction that may have the bound. That only offered this option for highly impacted wines. And then the spinning cone technology, you know, it was developed actually for ethanol reduction. And what they did was, with the spinning on a vacuum, you get the essence where most of your volatile aromas are. Then you get the ethanol, and then you get basically your high molecular weight fraction. They took that fraction, put it through a proprietary resin, and then you could decide to put the essence back or not. And they offered that as a treatment. I don't think they do it anymore, but they used to offer that as a treatment for smoke impacted wines. So here's my experimental design. And I just want to show you here, it's a little bit complex on this side. So what happened is I still had this 2017 wine from Oakville, and that I saw as low impacted. Then in 2018, there was the fires in Lake Mendocino County. And I got grapes that was a distance from the fire, but clearly impact. That was my medium. And then I got this from a vineyard that was very, very close to the fires and in the direction of the smoke. And we kept the press wine and the free run wines separate. Yes, your press wine can have more volatile phenols. Whatever haven't extracted yet, and you know, it developed an equilibrium between what's in the skins and the juice, or in the fermenting wine, is when you press, you can by mechanical force actually force more of the volatile phenols out. And when I say volatile phenols, I'm really talking about them as a group. Those that are volatile phenols and their precursors. You can force them out from the skins. So you want to keep your press fractions separate if you consider or think there may be smoke impact, and evaluate them separate and keep them separate. You may want to treat the press wine, for instance, if there's a low impact. Anyway, so what I have here is my high impact, my slightly less high impact, my medium impact, and my low impact. So this is all the free volatile phenols. There's a combo of all the free volatile phenols at that stage that I was analyzing, all added together. And the main thing I want to show you, irrespective of the treatment, the left one is always the control. You can see it was pretty effective, right? And really all of them decrease it. And in this instance, mostly molecular printed polymers work really well, then reverse osmosis, then activated charcoal funning, and then spinicone. But the thing is here, it did depend somewhat in the matrix. It wasn't always in this order, something to remember. Now this looks pretty good. However, when you go to the total, so this increases the free and the bound, then what you can see is that it doesn't look all that great. So basically, you're going to have not that it doesn't work that well as soon as you go for the bound. So we still do have some work to do here. So the main thing I want to get to is we did sensory. And if you look at the sensory, this is the control wine that saw no smoke. If you look on the left, this is the opposite to our smoky character. Ash was on in the mouth, pig with smoke was on the nose. Okay. Wine 3 and 4 was our medium and low impact. Wine 1 and 2 was our high impact. Irrespective of the treatment, the low to medium impacted wines could be treated and we could remove the smoke impact. So this is the importance of doing bench trials. And I think where we're going to get is we're going to try and say, okay, at this level, treatment is an option. At this level, treatment may not be an option, because you have to remember, you don't have to remove everything. You just need to remove enough that it's in the normal range so that over the lifetime of that wine, it doesn't develop smoke again. Okay, so basically what I want to say, we don't have a golden bullet. We're trying to develop methods now that's more specific so that it has a lower impact on the overall quality of the wine. And so that it can really own and focus more on the bound as well. So at this stage, we're trying to develop enzymes that can cleave the bound into free, and then optimizing resins to just remove the free and nothing else in the wine. Quickly, I know I'm out of time. I want to say this. What we're doing now is we're looking for more robust, cheaper methods for analytics. We're looking at baseline. We want to give you the two bookends. For the main varieties in California, what is normal? And how much do you need in the wine? How much do you need elevated before it actually impacts wine quality? So what's the threshold value in different wine matrices? And this is going to take us a few years. This is a big, big job. And we're going to need to do it for each variety for several seasons because of the huge seasonal impact. So basically, this is what we want to do. We can want to give you a baseline of what is normal and show you where your sample is. If your sample is above baseline, you have a higher risk. If it's elevated baseline, there's some risk. If it's medium baseline or lower, then your risk is almost nothing. It's never going to be zero, right? So we did some intentional smoking last year. We're trying to work on threshold values in Cabernet Sauvignon. We're going to try doing it for Malbec and Syrah, just because that's the grapes we got. But Cabernet Sauvignon is our main focus to start off with. I just quickly want to remind people, what we recommend is take a berry sample. Take it from berry hazen onwards, every 2 weeks or whatever, just throw it in your freezer. If there's a smoke event, it's too late to go and take a sample then. Then you have baseline for yourself. Then close to harvest, like a week before harvest, go and take another berry sample. And then you can compare those two for yourself while we don't have public baseline, and you can interpret your data better. We recommend small lot fermentations. Why? Because crop insurance looks at the free number. During fermentation, it releases the bound to the free, some of that at least, and your free number will more reflect of what's actually in your grapes. And obviously you can taste it. You can train people to taste smoke tank. It's not easy, but it's doable. If you're a grower, you want to talk to your winery and you want to have this discussion about what do you do when there's a smoke event, who does what, who pays for that, what, who is the sensory panel, and make sure that the people that's on your sensory panel can actually taste smoke taint. 20 to 25% of people aren't very sensitive to smoke. Obviously not the people that you want on your panel. I'm out of time. I will share my slides with you so you can read everything that I skipped over very quickly. I'm very sorry. I was, sharing too much information right at the start. Anyway, something else, if you do smoke taint tastings, Remember, there's a huge carryover. You need to rinse your mouth with water, wait 2 minutes before you taste the next wine, or everything will taste smoke impacted to you. Thank you very much.
Thank you, Anita. So we will be sharing the slides as long as those who present allow us to share them. And obviously Anita has offered. We are going to take a quick break. Let's take it until it's now 10:31. If we can come back around 10:37. If someone does have questions that they want to ask Anita during the break, I guess we could probably stick around and have people ask a few questions, but certainly feel free to take a break, and we won't start before 10:37 with the next presentation. Thanks.
Thank you, Anita. I did have a question.
Absolutely, go for it. I'm here.
Yeah. So it was about clarification, really. You said you said that in testing fruit, free and total is sort of the most labs do it, and it's the most economical. But then you said a little later, you said you absolutely need to do bound. And just to clarify, does total give you bound?
Yes. Okay. So that could be a little bit confusing. So yes, the total is free and bound together.
Thank you.
So if you do total, you do need to get the free number, because what you do is you subtract your free number from the total number, and then you know you're bound.
That's what I thought.
Yeah, but I mean, even if you just do total, and that's what you do for your baseline, and that's what you do for your grapes that get smoke impacted, you also get an idea of the total number. But I like to add the free. It just gives you, even though we know the free isn't that predictive, it just gives you another data point, because you're already with all the analytics. Even if you make wine and you taste it and you do the most extensive analytics that's out there, you still have, like, I don't know, 4 pieces of a 10-piece puzzle, and you're trying to make a decision and see the full picture. So I'm always like, every data point you can get. Individual bound is great, because then you know exactly what you're measuring. But like I said, the one gives you a very accurate but small window. The other one is more broader, but you don't know exactly what it's measuring, right? So I don't know what's best. Individual bound is great. If you've been doing that, keep on doing that. It's just that currently we have like 2 labs in the US that do that. There's the one lab, Australia, the Australian Wine Research Institute commercial lab does it well. That's it. If we have a 2020 event, we're going to be labs inundated. And I do need to say this. I do have empathy with labs. I think people need to realize that the equipment that's used to analyze for these compounds are extremely expensive. And the people that you need to employ to run them and maintain them are not cheap. And it's a skill set. It's not somebody that you can train from the street. So to have those people permanently being paid for and having extremely expensive paperweights obviously make no business sense, right? So somebody can't have equipment and people there for in case there's an extraordinary event like 2020, which none of us hope for. Right. So, I mean, there's more labs online that do analytics now than we had in 2020. There is more. Mm-hmm. But if we have another 2020, unfortunately, that's going to be a backlog. And if it's that extensive, I don't see us really getting away from that until we have better analytics that can cut down on the amount of testing, meaning like a sensor network, a sensor that can accurately tell you yes, no for risk. Because even in 2020, there's a lot of people that analyze grapes that probably didn't need to, or there's people that analyze grapes every time. There was a smoke exposure, I did my analytics. Smoke exposure, I did analytics. They should have just they could have thrown it in the freezer, some samples, but really the only one they needed was the one close to harvest, because the volatile phenols doesn't disappear. I know some people have done analysis in this, but Anita, I don't get the same number. With ripeness, it changed. Yes, because these things get bound. There's things that change, and we can't explain all of that because, once again, individual bound, look at 6 compounds. The overall, look at our drought tolerance efficiency of a range of compounds. And as those compounds change during ripening, we don't know really what happens. So this is why just take a sample close to harvest. That's your most important sample. And every time you have a smoke exposure, you're going to get more volatile phenols absorbing, right? There's no saturation level that we found. What we found is like the Australians in the beginning, they did stuff like take a bunch and actually put it inside a drum that had grass burning. And the smoke exposure was so excessive that it actually forced some of the volatile phenols into the flesh. Because most of the time you don't see it in the pulp, you only see it in the skin. So yeah, I think, we haven't seen an event where you do a smoke exposure, nothing absorbs because, hey, we've had enough, the grape says, but that doesn't happen. It will keep absorbing it. So that is something to think about. I have a few questions here. Wait. I'm in the chat. I'm looking at the chat.
Can I just also I made a comment
Yeah.
about getting baseline data this year. I thought that was really, assuming that, if we don't have smoke exposure, hopefully it's still maybe worthwhile for growers to consider getting baseline, especially for some varieties like Syrah.
Yeah, so Sue Ebler and myself is trying to do baseline. And we started last year. And obviously we did not include the Foothills last year. But we would like to include.
But we have
this
fruit
year.
for you.
So we do need, something that's representative of that grape growing region. So low, high topography and sort of spread around the region. And this is the 7 varieties we're looking at now. Hopefully I remember this.
Right.
Cabernet Sauvignon, Merlot, Pinot Noir, Syrah, Chardonnay. No, I'm wrong. Here we go. Cabernet Sauvignon, Merlot, Pinot Noir,
Chardonnay and Sauvignon.
Zinfandel,
Yeah. Oh,
Syrah, Chardonnay, Sauvignon Blanc. So 5 red, 2 white, because that makes up like 85% of the grapes that get crushed.
Hey, Anita, there's one quick question before we move on to Beth, and that's how big are the samples every 2 weeks prior to harvest that they should put?
So about a 300 berry, and this is very, very important. Whatever you do, and like small scale fermentations as well, you need to be representative. So this is why we say for micro fermentations, you take a bunch from at least 40 vines spread across the block that you're trying to represent. So for that 300 berry sample, you need from clusters inside the canopy, outside the canopy, top, low, bottom of clusters, and really spread across your vineyard. Because I can tell you, when we do intentional smoking, you have 2 bunches, and those inside the canopy and outside the canopy, very, very different volatile phenol numbers and bound numbers. The same for 2 vines next to each other. So vineyard variability is there. So really make sure that whatever you put in your freezer is representative. But 300 berries, you're good. You're good for your first analysis, and you're good for going back if you need to.
Anita, this is Clark Smith. Can I ask you a quick question?
Sure.
I wonder, I was sort of blown away at the Unified tasting some samples from Pure Fresh, which took over Purovina and kind of refined their ozone treatment. I couldn't believe the difference. And I just wondered whether you had been in contact with those people.
Yeah, so the thing with Pure Fresh, and Kerry Wilkinson did a study, and I've been talking to Pure Fresh, we're trying to get something together. The thing there is that if you look at the analytics, it does, it's an oxidizer, right? And it does oxidize, it seems to oxidize some of the volatile phenols. But if you look at the numbers, the difference isn't huge number-wise.
Well, but the sensory was amazing.
Yeah, but the sensory is different. But once again, I would say again, like most of the other techniques, if your impact is low, I think something like that has, we don't understand why, because this is the matrix impact. Those that we are measuring. So it could be because we're not measuring all the correct compounds, and we're just not seeing the impact on those compounds.
Right. That's why I really question the analytics altogether.
Yeah.
I think it's some other stuff.
Yeah, so we're still looking at that, and that's a huge problem. And the other thing is,
I'd encourage you to do so. I was really amazed.
Yeah, we are looking, and there's some stuff, but it's all unpublished. So, and it's not my work, it's some of my collaborators, so I can talk about it. But we're working on it, I promise you.
Thank you.
And the other thing is also matrix effect. It's totally possible that it's removing something else. There's other techniques out there. I don't want to go into specific companies, but that I've tasted wines, and some of it was, say, treatment columns. And the wine, there's a control, it went one treatment through the column, the other one went twice through the column. You look at the analytics, not huge differences. You look at it and you go, oh, would this even have a sensory impact? And then sometimes it's like, once through the column actually improved the sensory, twice not. So some of it may also be, it's removing something else than the volatile phenols in the matrix that's changing the perception of that smoke. I mean, that is something that we definitely saw. I mean, I think the ozone, the question is out there. It does seem to help on lower impact. Obviously, it's not cheap, but something to consider. Something like flash detant. People have been using flash detant, and I can tell you, even 80 degrees on a vacuum, and I know I need to get finished because I'm looking at Karen's picture looking at me, but basically, it doesn't remove a lot of the volatile phenols either under those conditions, but because of that massive extraction of phenolics and color and fruity aromas, it seems to hide the smoke in like a medium to low level. How long it lasts, I can't tell you.
Yeah.
But I'll hang around until the end if you want to ask me questions at the end. Okay, and I'm supposed to be the next person moderating, huh?
Yes.
Well, thank you for having this slide up. Okay, so before I steal any more of Beth's time,
I thought you'd get the hint, Anita, but you just
in
got
the butt, but luckily she's far away. So our next speaker is Beth Forrestall. She is a professor in viticulture here at the department, and we're very, very happy that she could speak to you today. So she's going to talk about the effects of variable irrigation practices under extreme heat conditions. Thank you, Beth.
Thanks, Anita. And thanks for your great presentation. It's really great to hear how much knowledge you have. It's so helpful to everyone and us hearing it. So today I'm going to talk to you about some work that I've been doing in the Lodi area, but just give you sort of a brief introduction about why I started this work as one of my first projects as a professor in the department. And coming from an ecology background and thinking about a lot of climate plant interactions, it's obviously going to be really, really relevant to agriculture to consider the impacts of extreme heat events. And I'm going to define it. I'll give you a specific definition for the site that I worked at and we're working at. But what it is just an anomalous event outside of what you would normally see in terms of 3 or more days above a certain threshold temperature. So in the foothills, it would be lower than it would be in Modesto if you're defining a heat wave. In Lodi, the way we defined it was 3 days above 38 degrees Celsius or 100. But again, there's acclimation potential and other things going on. But the reason why it's important to understand how a number of heat waves and the impacts of having greater atmospheric demand for water, which is going to be accompanied by higher temperatures, so higher potential VPD, vapor pressure deficit, and higher potential ET, drier soils, is that because they're anomalous events, just as smoke events, and they're actually very inextricably linked to smoke events too, as most of you know, the heat events, is that we don't know how to deal with them necessarily because we don't have the historical precedent for doing so. And so similarly, we know that we'll be coping. So this couples really well with Megan's work and with Ani's, but we'll be coping with droughts continuously. We know we're in the largest drought in the West that there ever has been in 12,000 years now. So we know this is ongoing and we know water resources are scarce. And so this is just projections for the next century and taking into account that we know that there will be atmospheric drought, which will impact soil moisture on the surface down into the column. And then another thing really relevant to the foothills is thinking about runoff too. We will not have, even though we do not have a huge dramatic change in precipitation, I think this last these last deluges in December and just thinking about how much variation there'll be in precipitation and knowing that they'll come in these huge dumps will be something that results in not having as much in terms of water resources. And so when I think about this in terms of heat waves, it's relevant, and I won't present all of this, but some of you probably here participated in a survey that I put out with USDA and thinking about how you respond to heat waves and the major, or whether there was concern and whether growers would use water prior to heat waves to cope with them. Because in conversation, that's what I know people do. I know there are other practices as well, but in terms of actual economic sense, most people just use irrigation as a means of cooling the plant and apply water before a heat wave, knowing that the plant can then use evaporative cooling and it cools the soils. And so that's why we did the experiment this way, is to understand how much water was needed to actually cope with heat waves and what impacts it has on berry chemistry, plant physiology, plant health long-term. And then also just thinking about the actual wine. We made wine from this as well. So as far as what we know about heat stress meaning for vines and berries, there aren't very many field studies. There are a few out there, some from Australia and elsewhere, but we do know that high temperatures affect berry chemistry and wine characteristics, an increase in vine respiration. So in some instances, this is variable results. Sometimes you see that there's less available sugar to be converted into alcohol potentially. And that's something else that we're working on in a more targeted mechanized or targeted experiment, thinking about mechanization or what is driving that. Lower yields. So we saw there's variable results there too. And then reduction in transpiration. If you don't have the water resources, it actually has a huge impact on vine temperature, canopy production, enzymatic pathways. So work out of Australia, Sodrez and Moran and Greer, they have found that actually you can have an impact that's 2 to 3 weeks post heat wave event if you have a really extreme heat event. And so we wanted to know that whether you would see that beyond a greenhouse experiment or see it in the field. And then also there's evidence for reduction in secondary compounds and a shift in the balance between what you'd expect between some of your soluble solids and phenolic compounds. So in the context of doing this in the vineyard, we had a multi-scaled approach, and it was largely collaborative, working with some of the Open ET, in addition to some work that's being done with USDA and the Macaron Lab. For the infield component, we did a lot with leaf level physiology, pre, during, and post heat waves, and I'll describe explicitly what our design was. So we looked at leaf temperature, conductance, photosynthesis, and then I had a postdoc working on some of the carbon assimilation and ET effects to see if you could use in situ ET measurements to be able to make decisions about irrigation using the forecast. We're also looking at very chemical and molecular responses. I'm not going to go into any of the molecular data, but I'll talk to you about the berry chemistry, the plant physiology, and the wine chemistry from our first sensory trial. And then also too, we're looking at this regionally to see if there's different impacts of heat waves on different cultivars. Everything I'll present today is in Cabernet. So as far as the site, I know this is sort of a stone's throw away from the foothills. Again, you're at higher elevation, but hopefully this is insightful in some way. So we worked in Galt, just outside Galt, at a Borden Hills site in the northeastern part of Lodi. And as you can see here, if we think about the number of days, you'll have to excuse me, I'm afflicted by allergies, as most of us are, so I'm a little hoarse. In Lodi, there's going to be a huge increase in the number of days above 38 degrees Celsius or 100 degrees Fahrenheit. And again, the reason that I picked this threshold is because it sat outside a distribution of days in the past that have been above the 98th percentile in terms of Tmax or maximum temperatures. So we're picking what is extreme based on a baseline of the past. I use the past 30 years because it's constantly increasing. So this is just to give you an idea of how much things will increase is we're going to have a number of days above this threshold that gets up into 50 or 60 or 70. And so this is actually appropriate for regions like the foothills, because similarly, you'll start approaching this as well. And so the way that this was set up is we collaborated with Gallo and we leveraged an existing variable rate drip irrigation system that they have set up in this vineyard. The vineyard has, and this is an important caveat to mention, is the vineyard has a lot of topography. So there's actually quite a bit of difference in the soils and some of the water penetration, which I think makes our results even more convincing in terms of the impacts, because we had so much heterogeneity in the site. And so we're replicating some of this in more homogeneous soils, but we had pretty striking results. So I should say the student who worked on this and really made it happen was Martina Galliano. She's a master's student, now a winemaker, head winemaker in Mendoza. This site, so here, if you look at these little, we call them pixels, they're 30 by 30 meters squared, 170 vine treatment pixels or blocks or squares. And each one of these, we had the capacity to alter the irrigation in. And the way that we did that is by implementing when there was a heat wave in the forecast, 2 days prior, we would start our irrigation treatments. I should say the background irrigation were decisions based on ET levels for a target of 60%, hitting 60% ET. That was something that we let, and because we didn't have as much control, but we let the growers or the management company in Gallo make those decisions. So we knew what the baseline irrigation was for all of these, but we were only manipulating irrigation before heat waves and during heat waves. So we increased in the blocks that we kept at baseline, so didn't increase irrigation at all in 4 blocks, 3 or 4 blocks. And so that was keeping it at baseline ET, 60% ET target. And then we did 2 times the baseline based on hours of irrigation per day for the second treatment, again, 2 days, and then throughout the heat wave event. And then we did 3 times that. So I know a lot of people's gut response, and based on some of our survey responses, thinking that doing 3 times the treatment in terms of 3 times numbers of hour for irrigation applications seems really high. I can assure you now, based on seeing what growers have done in the field from some of the data that I'm collecting and collating on irrigation and what they've done here, that isn't out of the realm of possibility for what's happening. It varies quite a bit by region, but it isn't unreasonable, and there is quite a bit of water used during heat waves, and it has a pretty significant impact. So I'm going to show you the data from 2019. This study we've replicated in 2019, the summer of 2019, 2020, and 2021 with some slight alterations. So I'm going to show you the 2019-2020 seasons, and then some of the berry chemistry data and yield impacts on that, and wine impacts or impacts on wine. And so the 2019 field season was relatively mild in the grand scheme of what we've seen in the past 8 years. 2020 was obviously quite different, but we had 2 major heat wave events, one pre-veraison and then one post-veraison, a little bit closer to harvest. And if you look at this, the way you interpret it is this is the irrigation that was ongoing. So quite a bit of water applied, not too uncommon for Central Valley viticulture, quite a bit of water applied throughout the season. And so this is daily applied irrigation here on the y-axis on the left, and then your maximum temperature. And you can see what we did again is prior to the heat event, we maintained baseline 2 times that. And I'll just call this the 2x treatment and then the 3x treatment. And you can see we did that just to visualize what the season was like and when the events occurred. So I'm not going to go into a ton of detail with the physiological responses, but obviously, since we use stem water, leaf water potentials as targets for planting irrigation, it's really important to note that even with the supplemental irrigation, we did see an impact of slightly less negative water potentials, but we never got, these were pretty well irrigated. We never, even with limiting irrigation, we never got to super negative values. That's changed. That's definitely different for 2020. And I think too, with the implications of having fewer water resources this year, even more so than last year, that will change as well. But we didn't ever see a huge lasting impact in terms of stress either. We'd always see sort of a transient impact and then eventual recovery, sort of a transient impact of having more negative stem water potentials than those without water, and then recovery. And we never found a great correlation between how negative the water potentials got necessarily in some of the berry chemistry. And so we think using some of the thermal data might be a better approach. But one thing I should note, which is most definitely having an impact, is the impact on net photosynthesis and stomatal conductance. So it makes perfect sense that you would have stomatal closure if you have water stress, related a lot to some of the things that Megan talked about. And so we were interested in whether this is something. So I'm just showing you one heat wave and just making note that there was a dramatic reduction in stomatal conductance, and it was directly related. So this is stomatal conductance, and this is net photosynthesis on the x-axis, and then this is the leaf temperature. And so we saw as the leaf temperature increased, which it did for those with less water, and even the 2x and 3x, there was a difference there, significant difference there for conductance. So at the warmer temperatures, the plant is shutting down. And that makes sense. But I should say too, that we never saw any indication that there was any sort of biochemical, permanent biochemical damage or damage to some of the photosynthetic apparatuses. There was rapid recovery. And one thing that we're looking at too, and this relates to some of the impacts on yield, is this year we collected woody tissue from all different organs of different ages and from the root system to look to see if these treatments over the past 3 years have had a negative impact on carbon storage throughout the vine. Because we want to be able to say you can potentially use less water, but what impact does that have on vine health going forward? And so we're looking at that too. So impacts on yield. Not too surprisingly, there was a negative impact on yield for the baseline treatment where there was no increase in irrigation at all during a heat wave. There is negative impact on kilograms per vine, grapes per cluster. And then also, I'm not showing this here, but the berries were smaller as well. And one thing that was interesting too, is that we did see a slight lower, albeit not significant, decrease in the 3x treatment. And what we really wanted to know and tease apart is whether there is some, not only, it wouldn't be surprising to see a negative impact of not having any water pre-heat wave, but also, is there a point where you're applying too much? And at what point are you applying too much? And does that have negative impacts, cascading impacts on berry chemistry and on wine? So this is the berry composition data. Again, there's mixed results of what you see in the literature in terms of whether you have an increase in Brix or sugar accumulation rates or not with heat wave. We saw it with heat impacts. We saw that there was, and that we actually, because we were targeting 25 Brix as our harvest, we ended up having to harvest the baseline treatment a week earlier. So we saw that there was pretty more rapid accumulation, even being a month after that second heat wave event, that there was that impact. We know too that you can have delayed sugar accumulation. We saw that in 2017 in some instances as well. But in this case, where there was really only that heat wave on August 15th, not right at harvest, that we did see the impact of less water as far as having higher Brix levels and approaching those Brix levels more quickly. And there was no difference between the 2x and 3x baseline as far as Brix levels or accumulation of sugar. Again, not too surprisingly, we saw that there was a higher pH and lower TAs for the treatment where there was no additional water. And you start seeing here too the separation between the 2x and 3x treatment, so that excuse me, the 2x treatment sorry, there are no labels on this one, but the 2X treatment, which is the green, actually fell out as having the lowest pH. And really with some of the phenolic compounds for this year is where you really see some difference between the treatments. Interestingly, the 2X treatment ended up being the one with the highest amount of anthocyanins, suggesting that just as we know that overwatering can have a negative impact on some of that synthesis. And so we saw highest synthesis of anthocyanins, and it was maintained to harvest post this second heat wave. And as you can see, it was most definitely an impact of the treatments here, because this is where we had our treatment, and then you see that separation. And then the least amount of anthocyanins were in the baseline treatment, but you saw this negative impact of overwatering as well in terms of anthocyanin content. And again, this has been found in previous studies as you see this decoupling in the relationship between soluble solids and anthocyanins, which I don't know that people necessarily always assume you'll have a certain level based on your Brix, target Brix, but just knowing that if you're targeting harvest based on your Brix, that depending on these different factors, just by altering irrigation during heat waves can have a pretty significant impact on that relationship between some of your phenolic compounds and your soluble solids. Another thing that I found to be pretty striking, and unfortunately we didn't have tannin data, tannin synthesis starts at flowering. So and these results suggest that actually heat wave 1 back here was what drove this response of having different levels of tannins. And heat wave 2 treatment didn't seem to have much of an impact at this point. Post-ferration, tannin synthesis is complete. Obviously you can have other changes, but degradation, but we saw that similarly, your 2X treatment, where you have that moderate application of irrigation before the heat wave, is where you had your highest tannin synthesis, and the lowest was in the 3X. And so we're diving into that a little bit more as well in an experimental context on campus. And we have the data to look at molecular, we have the molecular data to actually look at some of the upregulation of certain genes associated with synthesis and see what is actually driving this. Flavonols, we just finished processing all of these because we had initially not looked at them, but there was a massive decrease in terms of flavonol production as well in the baseline treatment. And that's also not too surprising and goes along with our other phenolic results. As far as wine chemistry, I'm just gonna go through this quickly and show you our sensory results, which we just finished, and we're doing analysis of the wines from 2019. Unfortunately, everything is backlogged in sensory. And so we were just able to finish the first batch of wines, and hopefully we'll do 2020 this coming fall. But at bottling, we did see this split in terms of having higher alcohol on the baseline, which goes along with having that higher Brix content. And that was really what drove the difference, but this is the baseline treatment. We did see separation in wine chemistry at bottling. So this is the baseline treatment, 2X and 3X. And I think more interestingly, you'll have to excuse this rather janky figure. I just got this data. And I just started and didn't plot it myself, but this is in collaboration with Hilary Heyman and Annegret Cantu. So the sensory descriptive analysis of the 2019 wines is also significantly different. And so this is doing it in 2021 and 2022. And this is just the first of a set of sensory studies, but we found that there was a significant difference between all three, this being the 3X, the 2X, and the baseline, and that the baseline was hotter, sweeter, more dried fruit, higher astringency, and had this, in some cases, this really strong cooked vegetative property. So likely not characteristics that you would necessarily desire, but I think most importantly, it speaks to the fact that even these practices that you use only during the heat wave events can actually have a pretty dramatic impact on your sensory profiles, and this is 2 years after bottling, so it seems to have a continued impact. So for 2020, I'm going to show you the results for that quickly. We had 4 heat waves, and actually 2020 was the either hottest or second hottest. It was globally the hottest growing season on record for the Northern Hemisphere. And in our region, it was the second hottest ever. So it was a pretty impactful, as you all know, due to smoke as well, and fires as well. It was quite impactful. And we had that really early heat wave, one in July that I'm going to talk about. That was the most extreme. One in July that I'm going to talk about a little bit in more detail in terms of impacts of dry soils. And then we had 2 later in the season and 1 right before harvest. The only difference in terms of our treatment, so that we could correlate it with some of the remote sensing data, was to actually expand the size of our treatment grids so that they were 60 by 60 meters and about 700 vines instead of it being by the 30 by 30 meter pixels, because we needed to be able to fit a whole pixel that could be used. 30 by 30 meters is MODIS and other remote sensing data or satellite data. And we wanted to be able to correlate that with ET estimates using other products. And so I should say that this was not an easy season by any means, due to both COVID. Luckily, our vine rows were at the perfect distance so that we could keep doing this work, but also smoke impacts. And I think it's actually an interesting caveat to say that we had smoke over the vineyard, and this relates directly to Anita's work. We had significantly depressed photosynthetic rates in terms of plant performance due to smoke in the air, which makes sense. But we had no obvious impacts on any. We tried all the wines several times, and despite having consistent smoke and having consistent high values for particulate matter, there was no significant impact, which I think speaks a lot to knowing that the research she's doing is being so valuable in terms of proximity to fire, not just having smoke overhead. So in any case, so I'm going to quickly move through this, but we had similar responses in terms of heat wave responses. I'm going to focus on a few single heat waves instead of presenting them all. But we did get, these are stem water potentials, we did get down to instances where there would be negative 18 bars. But again, we had recovery always, and we didn't see any split between the 2x and 3x baseline for this. Again, this is net photosynthesis shown in a different way, but I want to show this is net photosynthesis here, stomatal conductance here. So again, you see dramatic stomatal closure. The lower values means you have stomatal closure, but always recovery. Again, lower assimilation rates, but you always had recovery. And I'm showing the September one because it was the closest to harvest, the September heat wave event. Again, negative impacts on yield, not at all surprising. And also, this was a little bit of a strange year because so much more water was applied in general. And to recover from one of the heat waves, they applied quite a bit of water afterwards for a week. And so we did have some sort of a drowning out of some of those effects because of how much water was applied after the fact for the July heat wave, which was the most intense. Again, we saw some of the parallel responses in terms of, we saw no separation between the 2x and 3x treatment, which I accept after heat wave 3, which I tend to believe is due to how much water was applied. I'll answer your question, Elizabeth, in a second in terms of rootstock use. 1103P was used in this vineyard, and I'll tell you some of our ongoing work that we're doing to assess that. And so we had reduced anthocyanins in the baseline treatment, reduced tannins, but then recovery in the baseline treatment as well for 2020. some similar responses in terms of anthocyanins and total soluble solids. We saw a lot more degradation. And I should say they harvested a little bit later too, but we saw clear signs of degradation in anthocyanins, which was more pronounced in the baseline treatment. And then again, transient effects in terms of flavonols. And so just as far as a summary of the irrigation and heat wave impacts from those 2 seasons, there were consistent impacts on vine physiology, but there was always recovery post heat wave. And as I said, we're looking at carbon storage in these different tissues and different treatments. And so we'll be able to see if there's any long-term impacts beyond just having lower yields each year in terms of having that decreased assimilation rate and lower conductance. We always had lower yield impacts on the baseline irrigation and decrease in anthocyanin content and tannin content in 2019, decrease in flavonols for 2019 in the baseline, and transient decrease in 2020. And then for our first study, and we'll be doing the 2020 study this coming fall, as I said, we did see changes in wine chemistry and sensory perception due to these different treatments. And so what I think, and I should say too, for 2021, which I'm not showing you here, we also had continuous berry temperature monitoring and ET monitoring, or we modeled ET throughout the summer, and we'll be looking at when we partition, especially when we think about partitioning transpiration and evaporation from the soils, which I'll talk about in 1 second, how important that is in terms of where you stand at your current DT value and what that means for wanting to water and how much to water, because we know it's pretty obvious that you do need to apply water prior to a heat wave, and it can have quite a pronounced effect on vine physiology. We were watering, we didn't have control over the timing of the water, but there's evidence from studies in Australia that actually nighttime watering can be effective in terms of cooling soil temperatures as well. And we know that there's very clear effects on berry chemistry and the resulting wine, but we also found that the excessive water can have a lasting negative impact as well. So you really do want to be able to fine tune how much you are adding in those instances. And one piece that I want to mention as well is that there's really clear potential impacts of re-radiation of heat. And I know a lot of people saw this from the July heat wave in 2021, but we ended up cutting the irrigation off 1 day early during the heat wave because of logistical constraints. And just that 1 day with having there was cover crop, but it was dead and there was bare exposed soil. But just in that 1 day, we had very, very pronounced re-radiation effects, really high soil temperatures. And it wasn't the water stress on the vine that caused some of the damage. It was actually re-radiation from the vineyard floor, and all of the leaves on the underside burned, and a lot of the fruit was damaged, which is what led to a lot of the excessive water being used afterwards. So one thing that I'm also very interested in exploring a little bit more, and what we're doing with some of the remote sensing data and drone data, is actually partitioning how much is these watering events are driving transpiration and evaporation from the soils as well, and partitioning some of that to see how much of this re-radiation effect matters and what we can actually do about that when we think about vineyard floor management. Lynne, it was in all of them, because in the last day, we didn't water in all of them. So that's how I know too, there's that impact of the re-radiation that was beyond just the water status of the vine. The vine's water status were quite different, but we had this impact across all of the treatments because there was the higher soil temperatures, and there was this clear re-radiation effect. So that being quite relevant in terms of vineyard floor management practices. The one quick thing that I wanted to mention in terms of thinking about some of these climatic impacts on berry chemistry is this work I'm doing in terms of updating the Winkler study and variety specific impacts of temperature and vine physiology and agronomic practices on I got an Anita, I'll finish. I'll be quick. Climatic impacts and on vine physiology and berry chemistry. And so what we're doing is building models of temperature optimum for soluble solids and other compounds to assess what type of climatic and agronomic impacts there are in berry chemistry. And this is just a relationship for all AVAs in Napa, because that's where we're initially working with Cabernet and looking at the relationship between monomeric anthocyanins and their degradation and bricks, and being able to assess how that might be impacted by different climatic and environmental and physical variables. And with that, I just want to thank all of our collaborators and funders for this work. And I'm happy to answer questions I won't be able to stay through the end, but I'm happy to answer questions via email. And you can reach out to me anytime.
Thank you, Beth. Sorry, our next speaker has a hard time limit because he actually does give a class at 12. And it's all my fault because I'm sure I went over. And poor Dave is always last and paying for me stealing his time. Thank you, Beth. And please email Beth any questions that you may have. Obviously, we don't have time for extra question time right now. We're going to hand it over to Dave Block, the chair of the department for the last decade. It sounds really long when you say it that way.
It does.
And professor both in viticulture and enology and in chemical engineering. And like I said, he's going to try and be quick because he actually needs to get to his class. So any questions, send it to us and we will convey it to Dave later. And we will be available when Dave is finished. So for any questions for the rest of the speakers that's still online. Thank you very much.
All right. Can you see that? Okay, cool. So thank you, Anita, for the introduction. And I think when I was asked to give this talk at this time, I was thinking, well, I'm going to be just done lecturing in one class and running to another one, but I think we can fit it in. So a little bit of extra pressure there. But what I want to talk about today, and I will say a lot of this work was done with Anita and in her lab. So I'm sure she can answer a lot of questions as well after I run off to class. But what I want to do is talk about our work over probably the last 10 years or so in understanding and controlling phenolic extraction during red wine fermentation. And like I said, a lot of this work is done with Anita's lab. And I'm going to try and focus on our most recent results, especially at the end of the talk. Just moving some of the Zoom stuff away so I can see what I'm doing here. So I think all of us all of you who are making wines commercially could probably agree that ideally it would be great if when your grapes came in, or even before your grapes came in, if you knew exactly what to do to process those grapes and go through fermentation, et cetera, and end up with exactly the phenolic profile that you would like. Unfortunately, that's, even though red wine has been made for thousands of years, that's not really possible right now. And mostly that's because phenolic extraction in red wines is really complicated. There's a lot going on. And so understanding all of the implications of the things that you can do to get exactly the phenolic profile you want when grapes are changing in time during ripening, the grapes are changing between varieties, the grapes are changing from season to season. It's just very difficult to do. And of course, if you have enough experience with your vineyards and so forth, and enough harvests under your belt with those particular grapes, this gets easier to do. But the real question is, how do we do this on a regular basis? How do we understand what our processing should be to get the phenolic profile we want on a regular basis? So phenolic extraction is complicated. You have the liquid on the bottom during fermentation, the solids, the seeds and skins and so forth are floating to the top, to the cap. A lot of the extraction, or all the extraction, is pretty much happening in the cap or at the surface of the cap. The bottom is well mixed. The top is not really mixed at all. You can control the temperature of the liquid pretty well if you have a jacketed tank. You're not controlling the temperature of the cap at all with the jacket. We've done a lot of experiments with that, although you can control the temperature with pump overs or punch downs or cap management. And so because of this, the situation is very complicated. It makes it very difficult to understand what's going on and predict what's going on. The kind of phenolics I'm going to be talking about for the rest of the talk, I'm not going to be going into a lot of specifics, but just to say, in most of the work that I'm going to show you here, we kind of group things into anthocyanins or monomeric phenolics that give you color, and tannins. And we're going to make some distinction between shorter tannins that are more going to give you perception of bitterness, and longer chain tannins that are going to give you more stringency and come from more from the skins, where the shorter ones are more coming from the seeds. And we're just going to make that distinction for now. So we're not going to go down into more resolution than that in the phenolics. So the idea with all of the stuff that we did was, in order to control the phenolic profile in wine, we're going to need to understand extraction. So initially, when we thought about this, and this is work that we did with E&J Gallo wine initially, and continued on, well, with them and with Anita's group for quite a few years, probably 6 or 7 years in the winery. The first thought was, let's go into the winery and actually investigate some of the key factors like temperature and cap management and so forth in either our small fermenters or our larger fermenters. These are about a 30-gallon working volume. These are about 400 or 500 gallon working volume. And just see what impact these more obvious things have, like temperature or pump overs. And we could spend an hour talking about those results, but I'm going to kind of boil down 5 or 6 years of experiments into about 2 minutes of discussion. I'm going to do that with these 4 graphs that you see here. And these are kind of the lessons that we learned from our fermentations at the 30-gallon scale and our TJ fermenters, which are really well controlled. So let's take a look at this first, the upper left graph. And this is a graph of malvidin 3-glucoside, or one of the key anthocyanin in grapes. And what we did here is we looked at it as a function of the temperature of the liquid and the cap, and we could actually control both separately. But in this case, we control both at either 20, 25, 30, or 35 degrees Celsius. And the conclusion from that is, because these molecules are coming from the skin, that, and this is true not only of anthocyanins but other molecules coming from the skin, that skin extraction happens very early in the process. And even though the rate at which you get to a final level of anthocyanin is temperature dependent, the final level that we reached was not temperature dependent. And I'd say the exception to that was when you get too high in temperature, we started seeing degradation of anthocyanins. At about 35 degrees Celsius, we saw significant degradation. So skin extraction happens early, and the extent is not temperature dependent. Whoops, let me go back. Then we looked at catechin, which would give you some indication of what's happening with seed extraction, and we measured other things coming from the seeds and saw the same pattern. In this case, what we found was seed extraction starts later, and it's definitely temperature dependent. Not only the rate at which you get extraction, but the final level that you get in your wine. The next thing we looked at, and this is, I just show one example, but this happened with pretty much everything we measured, every kind of phenolic we measured, was that in our fermentations, phenolic extraction was not a strong function of pump over volume or frequency. And we tried all kinds of different pump over volumes and frequencies and combinations of them. And pretty much anything we tried, we didn't see much difference in phenolic extraction, which is interesting. And to the point where, one of the experiments we did that I'm showing here, just with malvidin 3-glucoside, but it's true of other things that we measured in phenolic profile, we actually, even when we didn't do any cap management at all, at the 30-gallon scale, we saw actually very little difference in the phenolic profile at the end. And what was interesting about this is the first time we we presented this to a large group of winemakers, I had someone say, well, I've done that experiment at large scale, and by accident, because my automated pump over pump didn't work and I didn't notice, and I came up with a very much a light pink wine and not a red wine. So what's the difference? Is there a difference of scale? And we'll talk about that a lot more in the rest of the talk, about what the differences in scale might be and why there might be in some cases a difference between what we see at 30 gallon and commercial scale. But I will say that after I gave some possibilities of what was different between what our experiment was and this person's inadvertent commercial experiment, I sat down and one of the other winemakers from the same organization came over to me and said, well, I've done that experiment on a large scale by accident too. And I saw the same thing you did. I saw a dark wine come out of that. And so we'll get back to that idea as we go forward, but it was clear in doing these experiments that we got a lot of interesting information out of them, but we still didn't understand everything that was going on. And so the next thing that we decided to do was to try and use the fundamental knowledge that we had and that we could gain to predict the behavior at a commercial scale. And this is mainly the work of one of our PhD students, Conrad Miller, who got his PhD in chemical engineering. He also had experience in winemaking and distillation and so forth, and brewing before he came back. So it was great to have him and his experience there. So let's talk a little bit about how it works. So what we're doing is creating a mathematical model that's based on fundamental knowledge and physics and things like that. And the details of this are not important, but I just want to give you an idea of what's involved in this. The key initially was to predict how temperature would vary over time and spatially in a commercial scale red fermenter, and how other things would, like ethanol concentration, would vary over time and spatially in a commercial scale fermenter as well, with the idea that extraction, when we get to adding in the phenolic extraction, those things are almost certainly from our experiments and other people's experiments going to be a function of temperature and ethanol. So if we're eventually going to predict that phenolic extraction with scale, we're going to need to know how temperature and ethanol vary over time and spatially. So how do we do that? Well, there are three components to this overall model. The first one is we need a model for how yeast cells grow and how that's a function of things like temperature and ethanol concentration. We published a model about 20-something years ago on this. And again, the details don't matter, but we can describe yeast growth in a wine background pretty well using the equations here for cell growth, for nitrogen utilization, sugar utilization, and ethanol production. And it actually works really well. The next part of the model is the kind of physics of what's going on. And so the first equation is the equation for mass transfer, things like diffusion from skins into the liquid. The second equation is the fluid mechanics going on for slightly compressible flow, meaning put in the idea that a warmer liquid is going to tend to go up because it's lower in density, and a cooler liquid is higher in density and will tend to drop down in a tank. And then the third equation is for heat transfer. The final thing that we needed to know is some of the physical properties of things in the fermenter itself, like the must. And a lot of that was not in the literature. So Conrad went out to the winery and just measured things like thermal conductivity as a function of how ripe the grapes were, and got that information. And then basically you could take all those things together and use a program called COMSOL, which uses finite elements, and the details of this are not important, other than you solve all those equations at the interstices of each of these triangles where all these things come together. And what you see here is actually half a cross section of a cylindrical tank. The top part would be where we're calculating what's going on with the cap, the bottom part with the liquid. And this is only half of it, but because we're assuming that it's a cylindrical tank, it's going to be symmetric around the axis in the middle of the tank. We just take that solution and rotate it around the tank. So that's how it generally works. The real question is, if we do this, how good are the predictions? And so what I have represented here are the predictions of what the temperature would look like in a 500-gallon fermenter. So small, like large pilot scale, small commercial scale. And what we're showing here is a cross section of what the temperature profile looks like. So what you can see here before a pump over, and this is about 3 days, predicted 3 days into the fermentation, is the liquid is being controlled at this temperature that's blue. You can see the scale here. It's small, but we're controlling at about 25 degrees, which is this color in the simulation. And you can see the cap is much hotter than the liquid below. We can't really control that with a jacket. And so you can see the cap is hot. Then we simulate a pump over here, and you can see the heat gets distributed through the fermenter, and then you start to get heat buildup in the cap. So this is what the model predicts. The question is, how close is this to reality? Because we want to be able to validate the model to know that we can use it to predict other things. And this is actual data for a fermenter that's that size and shape. This was done here in Davis. We published this work with collaborators in Vlad Jernick's group in Adelaide, and quite a while ago now, 12 years ago or so. And what you can see is, while it's not perfect, it's pretty close. We're seeing the same kind of behavior and the same kind of order of magnitude of cap to liquid temperature gradients and so forth. And we did a lot of other validation of this. I'm not going to go through it, but just to say the model actually works pretty well. And if the model works pretty well, that means that we can start to use it to predict how, for instance, the size of the fermenter and the shape of the fermenter might impact the temperature profile in that fermenter. And you can see for the first two, for A and B, these are, if I can move my PowerPoint stuff around. These are for 500 liters, so 125-gallon tanks, so small tank, either shorter, wider tank or tall, skinny tank. And you can see, regardless of the aspect ratio of that tank, the shape of that tank, we get pretty good control. This is 3 days into the fermentation, pretty good control of the temperature in the liquid, and not that much of a gradient between the cap and the liquid below. If we go up in scale from that 500 liters to 50,000 liters now, so that would be, let's say, 12,000 gallons. So it's a sizable commercial fermenter. What you can start to see is the shape actually impacts the temperature profile quite a bit. You're going to get cap being hotter in either case, but you can see in a tall, skinny tank, you can almost control the temperature at the 25 degrees you're shooting for. Where in a shorter, wider tank, you're not only aren't you controlling the temperature in the cap, but not in the liquid either, because you have less surface area to volume trying to control the temperature of that liquid with a jacket. When we get up to the 500,000 liters, so 125,000 gallons, so very large commercial tank, you can see you can't really control the temperature at all with a jacket. And that's why at that scale, commercially, most people will take the liquid out and send it through periodically through a heat exchanger externally and send it back in, sometimes in conjunction with a pump over event. So while we were looking at being able to predict temperature in a cylindrical stainless steel fermenter that's jacketed, we thought, oh, let's take a little bit of detour and see if we can use this to analyze temperature in a concrete tank and mixing a concrete tank. And I just thought this was kind of interesting to throw in. We did this in conjunction with Danielle Sereau at CADE, where she had concrete eggs that we could take measurements on. We used the same kind of approach with finite elements to model both the liquid temperature and the air temperature. This is with the white wine base. That's important. And we can model the temperature in the concrete shell. And what we saw is the data that we took are the circles here. The prediction is the lines, and we thought wow, we could actually predict pretty well what the temperature is in the shell or the outside of the shell and in the liquid. And, you know, when you buy concrete eggs, some of the claims that we've seen are that you get better temperature control because your concrete acts as a heat sink, and that you get better mixing because of the shape of the egg. And I can tell you from an engineering point of view, neither one of those conclusions is obvious. So we went and looked at that with our predictions. And I think just to give you the conclusion, what we found is this is the predictions of temperature in the egg. This is the prediction of temperature in the a similar size stainless steel jacketed tank. And what you can see is the concrete works better as an insulator than a heat sink, meaning you get your liquid, your wine heating up during fermentation. So it doesn't control your temperature better. And in terms of mixing, this is a little bit hard to tell here, but this is kind of the velocity of the liquid. You actually get more mixing in this jacketed stainless steel tank than you do in the egg. And so what does tell you is that maybe those reasons for buying an egg aren't the best reasons for buying an egg, but it could be that because of these things, or because of the chemical nature of contact of liquid with your concrete surface, you might get a wine that you like better and your consumers like better, which is fine, which is good. All right, so we're able to model temperature and ethanol concentration as a function of time and spatially. The question is, can we now add on the phenolic extraction part? So to do that, we have the model that I already talked about, and now we have to add in a model that phenolic extraction as a function of temperature and ethanol concentration. And once we have those two things, then we can use that comprehensive model to predict what's going on. So in terms of the model for phenolic extraction, we look at phenolic extraction as the sum of three parts: the release of the phenolics from the skin or seed cells into the liquid, the adsorption back onto solids, whether it's skins or seeds or yeast or any other solids that are there, and the desorption back into the liquid. And then the reaction, whether it's polymerization, which we didn't really account for because we felt that it might be happening in a longer time scale, or degradation, which we knew was happening and we did account for. So we actually take this and add mathematical equations to each of those steps. I should say we can measure these rate constants from the data we had that I showed you at the beginning. In Anita's lab, they did extensive studies on cell wall material and tannins and anthocyanins to measure the equilibrium constants. And then we could actually use that in the model to predict what was going on in a small scale, small enough that it's essentially well mixed. And what you can see is the points are the circles are the experimental data, the lines are the prediction, and we can see that actually at a really small scale, the model, just that model, just the simple model for phenolic extraction works really well. All right, so now we can take the model for temperature and ethanol as a function of space and time. We could take the model for phenolic extraction in a well-mixed system and now put them together into integrated comprehensive model. And the hope is that this model is going to predict what's going on at not only a small scale, but any scale and any shape of a fermenter. So we actually were lucky enough to have data on phenolics as a function of time and spatially, because we took a lot of that data, and this was, I guess it's not on here, but we published this probably about 7 years ago or so. This is work with Anita's group and my group. And what you can see here at the top is a cross section of what, I'm just using one example, but we did this for a bunch of different phenolics. For tannins, and how they will build up over time in the cap of the fermenter, and how when you have pump overs, those tannins get pushed down into the liquid and get redistributed over time. What you can see here in the top two curves is this is extraction of tannins in the cap over time, and the bottom two are the extraction, what's going on in the liquid over time. On the right is that using that combined model to be able to predict what's happening. And if you look between the left and the right, it's not perfect, but what we can see is there's pretty good agreement between what the prediction is from the comprehensive model and what we measured experimentally, which is great because there weren't a lot of assumptions involved in the model. And of course, there's still room to improve it, but it looks like it's good enough that we can use it to start to predict what's going to go on in a fermenter. What this graph shows you is if we just use that model for phenolic extraction without the comprehensive model, we would get a prediction of anthocyanin extraction that's the blue here or the blue here for tannin. And but what we see is that as you go up in scale, and this is probably true it is true as you change shape as well, the predictions that we get vary from what we would predict if we didn't look at what was going on spatially. And so that's why it's important to have the comprehensive model. All right, how can we use this? Well, the idea with this model is once we have a validated model, is you could use this as a winemaker like a GPS system. In other words, what we can do is we can put in the grape characteristics that are the characteristics of the grapes coming into our winery, or maybe we even know them from samples before they come into the winery. We can put in as our destination the desired phenolic profile and have the model tell us what are some of the different ways of getting to the phenolic profile that we want, given the grape characteristics that we have. And so this is kind of the general idea. We're not there yet. We're working on making the model simpler to use and faster to use. And then I have a little asterisk here because the other thing that we're going to need is fast measurements of grape characteristics that are in the model. And these include the total phenolics that are in there, meaning total tannins, C tannins, total skin tannins, and total anthocyanins, as well as the composition of the cell walls that have a lot to do with the absorption and desorption. And this is going to be things like lignin and pectin concentrations and so forth that Anita's lab has published, and how that affects the extractability. So we do have an AVF proposal that's being considered right now, using non-destructive fast ways of measuring all these things. So that could be, grapes come in, you do this fast measurement, put it into your app, and have it, along with the model, tell you what you might do to get the desired phenolic characteristics. And so if that work is funded, we'll go forward and try and come up with the fast ways of measuring those grape characteristics. So let me just give you examples of what this might look like. If, for instance, you were maximizing the skin tannin, wanted to maximize skin tannin. One of the things that the model shows us, and this is at, let's say, the 2,000 gallon scale, is that if you do no pump overs a day, the model predicts that you get this level of skin tannin. If you do 1 pump over a day, you get the blue line. And if you get 8 pump overs, you do 8 pump overs a day, you get the yellow line. So I think it's not an obvious thing that somewhere in the middle, there's an optimal amount of pump overs that you would do in order to maximize skin tannin. In a second case study that Conrad ran, what happens if you wanted to not minimize C tannin, but minimize the fraction of C tannin compared to your total tannin that you extract? And what we find from the model is this is at 2 different scales. A small scale, let's say 100 liter scale is this one, and 8,000 liter scale is the green one. As you increase the number of pump overs, even just a little bit, you can minimize the fraction of C tannin that you extract. And finally, what Conrad did was go back to this idea of why, in some cases, at a commercial scale, like at a research scale, if you don't do pump overs at all, why do you sometimes get extraction and why other times you don't? And what he found was by simulating tall, skinny, small tanks and shorter, wide, larger tanks with the same height, is what's really important is the height of the liquid that's underneath the cap. And so what he found was, for regardless of the scale, if that height was similar, we predicted that you got a similar type of extraction of anthocyanins. Okay, I'm running out of time, but what I want to do is just tell you where we're going with this. And where we're going with this is, in addition to working on that kind of app kind of system, is seeing whether we can use this information to intensify a process where people have been making red wine this similar way for thousands of years. So the idea is, could we do this and make a really great red wine in 3 days instead of 7 days in the fermentation, and have similar sensory characteristics, similar phenolic extraction, and so forth. So we're not going to go into the details of this, other than say, Conrad also worked on speeding up the yeast part of the fermentation. He was able to show, by doing very controlled nitrogen feeds throughout the fermentation, that he could go from a fermentation that finished in 300 hours to, say, one that finished in half the time. And I'm not going to show you this data, but with very minimal impact on the sensory characteristics of that white wine. So then we thought, well, if we can speed up that part, what about speeding up the phenolic extraction, see if we can get that to go from in half the time. And we did this. This is work by Anna Yao, who just finished her master's in my lab. And we looked at, could we do this by putting all the skins and seeds in a column that you see here, and just flowing either juice or wine through it. And, without going into any of the details, I'll just say we have some results that don't look that promising, and some like these that actually do. And in this case, the green is actually sending the wine through a column. The reddish orange is in a traditional fermentation at a small, albeit small scale. And what she found is, under certain conditions, she could get that extraction with flowing through that column to happen in about half the time. So there's still a lot of work to be done in there, but it looks promising that at least it's a possibility. And the reason you would potentially want to do your fermentation half the time is that could reduce your capital outlay, because you could potentially turn the tanks more often in your winery and use them more than once or twice in a season. So to summarize, we came up with a model that helps to predict the temperature and phenolic profiles over time. And having this kind of model can help us figure out how to optimize our fermenter design, or for a given fermenter, how to optimize our processing conditions to get the phenolic profile that we're looking for. So it's not completely there yet, but we made a lot of progress in the last couple of years. And one of the things that we could use that information for is to help intensify the red wine process, to mean that you need less equipment in your winery. So with that, I'd like to acknowledge American Vineyard Foundation and Gallo and the Ernest Gallo Endowed Chair for funding this research. And this is a list of all the people who did the work and collaborated over the years. Especially want to thank Anita and Conrad Miller and Anna Yao for doing the work. And thank you for your attention.
Thank you, Dave. I'm going to assume you don't have time for questions, because I'm already thinking you're running to class.
I'm going to get my exercise today. I'm going to close my exercise circle on my Apple Watch for sure.
Thank you so much, David.
Oh, my pleasure. And my email is dblock@ucdavis.edu. I'm happy to answer questions by email, and Anita can also answer questions on just about everything I talked about as well, even if she doesn't want to admit it.
Yeah, don't ask me about the formulas.
Thank you.
Thank you, Dave. We really appreciate you squeezing us, and good luck with class.
Thank you.
Okay, so that ends today's program. And so let me ask, is there anybody that have any questions? I know Beth had to drop off. Dave obviously is running at the moment, but Megan is still here. I'm still here. Lynn is still here. So if anybody has have any questions, this is your time to ask it, but you can email all of us if something only hits you later today when you have your glass of wine. What I also want to say is we do have upcoming programs, on-campus programs is starting up again. We had our first in-person program. It was a hybrid in March. That was about red blotch, grapevine disease. And we have our next program coming up April 8th, so next Friday. And it's actually smoke focused. So it's all about grape smoke exposure. Basically, as I suck at giving you all the information you need in 30 minutes, as you've noted, what we're going to do, this is a long day, and basically what I want to do is do the science, more time focused, and train. It's really focused on sensory. So this is only in person because the sensory is a huge component that you can't get from online. So the idea is I want to train people how to evaluate for smoke. It's actually pretty difficult. How to set up your own training or evaluations in your own environment. We actually made excess wine and bottled it in 2020, so I can send you home with reference wines. We're also going to do actual evaluations after we trained you and see how well you do, hopefully in real time. And I'm also going to go more focused into the different aspects, things that I couldn't really cover, really more into the mitigation trials that we're doing, both in the vineyard and in the winery, and others have been doing in the world, not just a few summary slides, also more into the work we've done on microfermentations, how to speed them up, how to relate that, how do they actually relate to larger fermentations for predictive power, to predict smoke impact. And we're going to have a winemaker panel of people with a lot of experience in working with growers, making harvest decisions, and actually making wines from grapes that are smoke impacted. They're also bringing quite a few wines to taste. It's going to be excessively taste forward, that's for sure. But so if you can make it April 8th on campus, we also have a program honoring Andy Walker in May, I think the 19th of May. So we would love to see people in person again. Any questions now that my monologue is over? Okay, here's a question. The sprays for grapes. Yeah, so at this point in time, we think that the sprays, so currently none of these sprays have specifically been developed for this application, right? So this is things that's already out there being used for other purposes that we're actually trying to see, can it actually help with grape smoke exposure? At this stage, it seems those sprays are just a physical barrier. So if you have a berry and it's fully covered in something else, and it actually has some affinity for the volatile phenols actually absorbs onto this barrier. And this is why that barrier actually have to be rinsed off or removed before you can make the wine, because it seems that during the winemaking process, whatever absorbed onto that barrier can actually then be released in your grapes or during your fermentation process into your wine. So currently we are working on, this is also part of that SCRI grant that works on the sensor networks, but it's just a smaller fraction of it. And this is specifically Oregon State University is working with the USDA there to look at proprietary barrier sprays developed specifically to absorb volatile phenols and have a high affinity for volatile phenols. Some sprays seems to do nothing, so they're not an effective barrier, and some things seems to make it worse. We don't really know why. One of the reasons we think is that it doesn't dry properly, so it's wet on the outside of the berry, increasing the volume and absorbing onto that, or in some way or form, it's almost a conduit into the berry. So I wouldn't just spray things. That is really dangerous. Currently, the only one that shows seemingly repeated efficacy somewhat is kaolin, but there's a lot we still need to figure out. And Tom Collins is doing a lot of work looking at time of application, how often do you need to apply it, is there a practical way to remove it before winemaking? And all these things are preventative. You never want to apply something while there's smoke in the air. That seems to be a bad idea. Okay, I have another question. I know this is just thank you. Okay, so I think we are almost at 12. If there's no other questions, I'm gonna want to thank for everybody that's still hanging online, waiting to have lunch. We really, really appreciate you joining us today. Thank you, Lynn, for helping us organize this. Karen and Caroline that do all the logistic work that I wouldn't even think about. Thank you, everyone. Hope to see you all soon in person. And thank you for our sponsors for making it possible that we can do these things for you at free. Thank you.
Thank you so much. Have a great day, everyone.